Syslog and SNMP. Monitoring your network devices is a really crucial part of network operations. It's one thing to go ahead and get your devices configured, but without monitoring them and having a sense of what the actual performance of your devices are, then you're stuck at the mercy of your end users in your organization telling you whether there's a problem or not. And at that point, you might not even know where the issue is, and sometimes your end users might exaggerate a little bit, which causes some problems with trying to actually troubleshoot. And this is where monitoring protocols like Syslog and SNMP come into play. Syslog is an awesome way for devices to tell you what's going on. A lot of times, if there's an issue, it's going to be sending out red flags with Syslog messages saying that it's having a problem. If it's overheating, it's going to end up telling you so. If there's a spanning tree convergence issue, or if there are a lot of events going on, then syslog messages are probably going to be generated, and you'll be able to reference those to see what's going on. Even after the fact, evaluating a situation after it's already resolved, you can go back and review your monitoring and your log messages to understand more closely what actually happened, so you can help prevent that in the future. And similarly with SNMP, that is actually a very flexible and useful protocol where you can not only just monitor your devices, but actually do configuration remotely. And since it is programmatic, you could actually set up applications to where things can be automatically adjusted and changed based upon certain conditions. So with that, let's go ahead and jump in and take a closer look at how SNMP and Syslog protocols work and how they're used here, and how they apply to the CCNA exam topics. So first up, let's talk about SNMP, the Simple Network Management Protocol. So SNMP is a defined protocol, and it typically uses UDP 161 for SNMP and UDP 162 for SNMP traps. And we'll explain the difference between those in just a moment here. Generally, you'll see three versions in use: version 1, version 2C, and version 3. Version 1 is hardly used at all anymore, just because it offers essentially no security whatsoever. The version 2C is much more commonly used. There is a version 2 and other subsets of version 2, but version 2C ended up being the primarily used version here and is most widely implemented. That generally, if you see version 2 on your device, it's actually talking about version 2C. A lot of people might reference it as version 2, but in reality their devices are probably running version 2C. And then there's version 3, which introduced a lot of security features into SNMP. See, SNMP used to have this funny nickname of "security is not my problem." And that's because there's just not really any security built into SNMP version 1 and version 2. That it's expected that the management line, the interface, or the circuit that's used to exchange SNMP messages, that line is secure, rather than having in-band management and expecting that the protocol will provide our security there. And that's where version 3 added a lot of excellent features here for encryption and authentication on both sides, so that you can actually secure the protocol here and not have to worry about having an out-of-band management line that you must secure in order to declare your protocol communication secure. There is some terminology used with SNMP that we should go over here that you'll end up seeing pretty often, and that you'll want to know what these are. An MIB, you'll see this referenced a lot. That's a management information base. See, a SNMP works in object identifiers, UIDs or OIDs. That OIDs are numbers in a dotted decimal kind of notation that you'll see, 1.1.2.6.7. 4.1.1. And these can be arbitrary length. These could be very long, and they are, separated by periods. And what these are is it's a hierarchical tree structure, and we'll take a look at that in a visualization in the next slide here. But what the management information base is this translates our UIDs into the actual information that's being queried from the device, where you go ahead and have a network management server here, which is some computer or some server that is hosting monitoring software that is actually doing SNMP polls. It's doing get operations for your SNMP and is telling your managed device, your router or switch, and specifically the SNMP agent, which is the SNMP software running on your managed device, that it is telling it to gather the value for a particular UID. And that the MIB tells us that this UID is representational of the traffic inbound on a particular interface, or of the particular configuration of OSPF, or of the neighbors currently there, or of the IP address configured on an interface, etc. That it's telling us what these numbers and what this hierarchical structure actually represents. That's the MIB. And that, unfortunately, there's not actually a standard out there for the OID structure, that it is dependent on the vendor to go ahead and develop their own OID structure for their devices, and then go ahead and release an MIB, the management information base, to be able to correlate those two together to understand what these OIDs actually are, how many OIDs there are, and the format and syntax of them, so that we can understand what information we're actually querying. And then the last two items here, we had just mentioned these, is the SNMP manager. That is your SNMP server, your device that's actually performing your get and set operations. That's telling your managed device, your router or switch, to go ahead and set a specific value to an UID, or to get the value of an UID. And that it is on your network management server, your NMS. That also traps. Traps are messages that are originated from your managed device and sent to your network management server. These are generally alerts of some kind, notifying of an emergency situation in some way. Usually, it might also be just some arbitrary information that's being sent over, but it is a trap, and that on your managed device, on your router or switch, you need to direct those traps to somewhere. It has a destination IP address because it's using, UDP 162 by default to go ahead and send these traps. And it needs to have a destination IP address, and that destination will be your network management server, also known as your SNMP manager. And that an important distinction to make, and I mentioned this, is that your managed device is one thing. That's your router or your switch, but the SNMP agent is actually software running on your managed device, that it's receiving these get or set messages, and it is querying some information, gathering some information from the operating system of your managed device, and then sending that back or setting it as appropriate given the message that's received from your network management server. And I did mention this here a couple of times, is that it is possible to set information with SNMP, that I can go ahead and set the IP address on an interface by SNMP, by sending an SNMP set message over to my managed device, which is great because that allows for potential automation in your network to go ahead and use SNMP to configure your devices, as long as you have SNMP set up on your devices and that connection there to be able to do that. So moving into the next slide here this is a sample hierarchical structure of an MIB, of a management information base. So we have just, the root of the tree here. And then we go down the tree if we want to go to, the TP link specifically down here. That, this is 1.3.6.1.4.1. And then there's some number here, the 11863, and we see that here. It's 1.3.6.1.4.1.11863. And you see there's not really any defined structure here. It is arbitrary, and it is set by the vendor, that they're the ones who go ahead and create this structure and define what our UIDs actually mean. So the difference between the SNMP versions here, SNMP version 1 and 2C only support really minimal security. They only validate the source with a community string. So you'll see that referenced a lot, a community string, where in your device, in your switch or your router, you'll need to go ahead and set SNMP and set it to be a certain community string. And then typically you can also set that only specific source IP addresses are allowed to poll the device for SNMP information. And then you can typically also set whether it's, read only or read write access, whether they can do get and set or only get operations. And that the community string, all it really does is it validates the source, is it tells our network management server that this device is actually the SNMP agent that we're looking to communicate with. It's just a clear text string that is sent across. Version 1 and version 2C actually don't even encrypt that community string at all. They just include it in their communication. Version 3 introduced authentication and encryption. So you can use username and password, and it will also encrypt its communication. And this is defined as auth and priv. That priv is for encryption. In your Cisco configuration, you'll see auth priv or auth no priv, no auth, no priv, to say that there's no authentication, no encryption, or that we want to authenticate but not encrypt, or we want to both authenticate and encrypt. That's how you end up seeing referenced in the Cisco configuration. And the SNMP, like I had said, it's most commonly used for monitoring, that you generally are polling your devices. You can get a whole wealth and slew of information from polling your devices for SNMP, that typically just about any bit of information that you can get out of a show command from your device, you can go ahead and poll with SNMP and get that information back. Almost. There's some that you can't, and it depends, of course, entirely on the vendor's implementation and whether they have decided to implement the SNMP UIDs to allow for polling of that information. But this can give you a lot of visibility into your network and allow you to alarm and alert you, the network admin, of certain conditions if things are outside of norms or outside of the expected values. But it can be used for management, that you do have the ability to set values by SNMP. So you could have automated remediation of certain situations by sending an SNMP set back. Typically in my environments, I don't see that we use SNMP for management. There are other more robust protocols and methods out there for managing your devices in a centralized fashion, that using SNMP is a little cumbersome and will vary a lot from vendor to vendor. So it's just not something that I see implemented often, but it does happen, and it is out there. And then specifically for the CCNA exam topics here, talk about how this ties into your studying, is that we just need to explain the function of SNMP in network operations, and that's what we should be able to describe here. So moving on over into syslog. So syslog is logging, but specifically syslog is a protocol that is defined in RFC 5424. or at least the most recent revision is defined there, that by default, Cisco devices use UDP 514 to transmit syslog messages, that it is a connectionless protocol. I have down here a Wireshark capture of a syslog message, that syslog transmits plain text unstructured message data, and it does also transmit a facility and level. And we'll talk about what that is in a few moments here in the next slide. But what do I mean by plain text unstructured message data? Is that we see down here, the last line here, the message. So it tells us how long the message is 71, and that here is the syslog message that was sent. That this is just a text string. This is not a structured data. This is not giving variables and their values. Is that this is just a text string that we have here, the timestamp, and we have the level here. That this is a level 5. Now, mind you, this is from a Cisco device. So syslog messages will look different based upon the vendor that is sending them, that the actual message content is not defined in the RFC, that just the protocol here for sending the syslog is defined in the RFC. And including the, timestamp here, you don't have to include that in your syslog message, but you can, and same thing in the text here as well. But this syslog message, this is telling us that we have interface fast01 that changed state to administratively down. That I went into that router here and went into that interface fast Ethernet 0/1 and did shut. And that generated a syslog message here. It generated a message of level 5, saying it is a notice level, and we'll see how that matches up to the other available levels in a moment here. And it is telling us like what kind of message it is here, and as well that it is a link message, and that it is a link level 5 message. It's a notice, and that specifically it's saying that it changed. That this can be helpful when monitoring syslog for Cisco devices to know what kind of message is being received, so you can alert based on certain text strings and be able to be aware of when important things come through. And then you have the actual text of your syslog message there, of course. So moving into our facilities and levels here is that the facility is actually something that tells you, from what source, what software on the device actually generated this message. And going back here to the Wireshark capture real quick, we see that this is facility local 7. That's reserved for local use. In Cisco devices, it does not change the facility, that the facility is a user configurable item, that all messages originating from that device will use the facility that is configured, and by default it uses the local 7 facility. And that this is something that you can configure. Local 7 is the facility number 23 down here. Some devices will go ahead and use these facility numbers. These facility numbers are actually defined in the RFC. And as well as the levels here, as that these descriptions are taken from Cisco here. But the facilities are defined in the RFC, but not all devices use them. Like I said, Cisco devices will default here to local 7, but that you can configure that to others. Your levels here, the lower level is more urgent. The level 0 is an emergency. This is typically a trap or an alert that's sent out saying that it's a last little cry for help, that something urgent really just happened. I am no longer usable. It's an emergency. An alert is level 1, critical level 2, errors level 3, warnings level 4. I would make sure that you know this table, at least the keywords and their level, how they match up there. I see these questions on the Cisco exams all the time, asking the level 3, what does that correspond to? And it ends up being an error. So I would know these in order to make sure that you're aware of this. And the order does also matter as well, because when you set for logging of level 4, then all messages with a level 4 or lower will be logged. Then when you set that in a Cisco device, it's of the logging level and lower will be logged. So if you set logging level to debugging, great. All of your debugging, informational, notifications, warnings, errors, critical, all of that will be logged and show up in your syslog. And that can be very important because that can be a lot of logs. And you can overload your syslog server. Typically, syslogs are sent to a syslog collector. And that's what we saw here, that our syslog collector here is at 10.122. And that the device that this is originating from is 10.121. These both happen to be Cisco devices, that they are in GNS3, and I was just generating this log as a example, but that these will be sent to a syslog collector. You don't necessarily have to use UDP. It can be TCP in a connection-oriented sense, and that there are other ports you can use as well, that this is a configurable item, but that this will go to a syslog collector. So if you are logging at the debugging level, that could be thousands of logs a minute. It could be hundreds of logs a second or more. That you could be seriously overloading your syslog collector, and you might want to be aware of that before you set your logging level here, that generally the types of items that are logged is something that is configurable, but we won't be going over that here today. Thanks so much for going through this with me. Just like the others, let's run through a couple of practice questions before we end off. First up, what is the name for software running on a network management server that pulls SNMP from managed devices? Is it an SNMP agent, the management information base, the SNMP manager, or is it just SNMP? Now, SNMP agent, this is the software running on your managed device that is gathering the information from your managed device and sending that back to your network management server. The management information base is what correlates your OIDs to your actual information on the managed device, and that SNMP is just the simple network management protocol, and that the software running on your network management server is the SNMP manager software C. And finally, what syslog level corresponds to an alert level message? Is it syslog level 1, 2, 3, or 4? Well, I just want to bring up the table here real quick, that here we have our emergency is level 0 and alert is level 1. So the answer here is A, level 1. I hope that this has been informative for you, and I'd like to thank you for viewing. Quality of service. Quality of service is a feature that most routers support, that it allows for the prioritization of certain traffic so that during times of congestion, we can make sure that our most important traffic is allowed through first and guaranteed that certain amount of bandwidth that's needed. Things like our mission-critical applications, our voice and video communications. That we want to make sure that these very sensitive applications and very sensitive traffic are allowed first or guaranteed a certain amount of bandwidth so that we maintain our quality of service and we ensure that the things that are most important to us are actually getting through. Specifically, the exam topic for this asks to explain the per hop forwarding behavior, and that's what we're going to go ahead and do. That quality of service is something that is configured per hop, that it is configured locally on each router, and that it does not necessarily act the same from router to router. That although we can mark our traffic so that we can try and treat that traffic flow similarly throughout the entire line or throughout the entire circuit, it doesn't necessarily get handled in the same manner at every hop down the road. So let's go ahead and jump right on in. So quality of service, as I said, it allows for the prioritization of traffic to be forwarded during times of congestion. So that is to note that quality of service generally does not have any effect if there is no congestion on the line. That if we're never getting into the software queue, then our traffic flows are going to generally be handled in a first in, first out basis. And that quality of service, as I said, is configured per hop. And it's configured specifically in Cisco devices with the modular QoS CLI, and that's MQC, as you'll see it abbreviated in a lot of documentation. That this is the tagline that Cisco has given their method of creating class maps and service policies, of identifying and classifying our traffic, and then adding some kind of action to that specific classification of traffic. And in general, on Cisco devices, QoS involves 3 processes. It is the identification of the traffic that we want to apply some special handling to, the classification of that traffic to say, now that we've identified it, in what class does this traffic now fall? And then finally, for that class, what do we want to do with it? What kind of action do we want to take? Do we want to schedule that traffic specifically and have it come out first? Do we want to shape it to make it so that traffic, in the event it's trying to move too quickly, that there's too much throughput, that we want to queue that traffic and only release it out onto the line at a specific rate? Or do we simply want to police it? The policing is just dropping of the traffic that goes over the specified rate. And we'll cover that a little more in the upcoming slides here. That this little, animation, or not animation, but figure here kind of shows a little bit of what we're doing, that each of these colors can represent different traffic flows. The green might represent a voice traffic flow, and red might represent our regular web surfing traffic, or purple might represent that, and so on. That in the beginning here, we have our policing and our markdown, that, it'll go ahead and drop traffic that's coming through too quickly, like these green flows right here, and that the purple flows here looks like that these just didn't even match against an ACL through our admission control, that, that's just not even allowed, and that we can go ahead and schedule our traffic to queue or drop it. That we can queue up this traffic if it's moving too quickly, or we can order it so that it is flowing out onto the line in a specific order to make sure we get our most important traffic out on the line first. Or we can shape it, which will end up being the same thing as queuing here, that we shape it and queue it such that it's only released at a certain rate, and then link-specific mechanisms will really just apply to your hardware queue, that for your individual interfaces on your router here, right? Say you've got several interfaces. Each of these interfaces does have a hardware queue as well, and that queue generally works in a first in, first out mechanism, and that queue is very small. It's really a hardware buffer for your interface to where the traffic is placed before it is actually transmitted directly out onto the line. So let's start off with our first process here of identification, and let's move into the next slide with that. So our identification and classification. So traffic can be identified using several different properties. That you could use your source and destination addresses. You could use the protocol that's being used. For example, for SIP, for your voice over IP, or your RTP, real-time protocol, for your voice over IP or video traffic. And then we could use our DSCP marking. Maybe our traffic has already flowed through a router or a device which has marked that traffic. That our DSCP marking is something in our IP header here. We've got the TOS field, an 8-bit field, where we have our DSCP domain. That stands for Differentiated Services Code Point. And this is a table here indicating the different levels of DSCP that we have available. and the binary equivalent for these 6 bits that are right here. And that for our voice traffic, our best practice is going to be to mark that with EF, that's expedited forwarding. The CS0 here, that is the equivalent of best effort, that is BE for the all zeros. And then you have a whole lot of different intermediate levels here to where we can go ahead and mark our traffic. That this is mostly useful for our identification and classification using downstream devices or upstream devices. See, the identification and marking of your traffic, changing this DSCP value here, that takes CPU cycles, and that is a software-driven process that if you have a lot of traffic to go through to identify and to mark, that can really put a strain on your CPU, that you'll want to make sure that the device that you're doing this on is capable of handling that amount of CPU load. This is also generally why it is best practice to mark your traffic as close to the source as possible. For one, you're going to be dealing with less traffic because it's not all aggregated together. It's not all of your business traffic that's aggregated together and you're trying to mark it all only at your firewall at the edge, but instead at the phones or at the individual routers at your departments, that you can go ahead and mark your traffic there such that you have less to deal with. Your process for marking this is more distributed, but then also so that you can go ahead and handle that appropriately throughout your organization, that you can just use your DSCP marking to go ahead and choose how you want to handle that traffic. Perhaps your EF, your expedited forwarding traffic, that is actually your mission critical application traffic, that's for your transactional database. Maybe you're an e-commerce website and that you have these transactional database traffic that needs to be really ensured that's going to get to its destination appropriately. The things that are higher here in your table, that these are generally for routing protocols and routing information, that your control information, your control plane traffic for your routers, that is very, very important traffic, even more so than your voice or video or mission critical application traffic, because if you don't have routing information going throughout your network, well, then nothing is going to work. Say somebody hacked into your database and is just flooding your network with an incredible amount of transactions and is making it so that you're sucking up all your bandwidth and that you can't even get your OSPF hello messages in between your devices. And now your neighbor relationships are going down and you can't even route around your network now. That's something to consider, that is a very important traffic flow, is your routing protocol information. And that you can use other things, of course, for identification of your traffic, that there's a whole slew of items that you could use. Basically anything that's in an extended access list and extended ACL, you can go ahead and use to identify your traffic in the modular QoS CLI. So now that we've gone over our identification classification here, I would be aware of this table. You don't need to necessarily know all of these guys, but at least be aware that expedited forwarding is the decimal 46 and that IP precedence 5. So the IP precedence, by the way, is the precedence value here. It is the three bits right here that defines the IP precedence, and that the decimal value is the decimal value of the whole DSCP binary 6 bits here, and that the binary here, that you can see that we've got 101 and that is 5, and 101 and that's 5, and then we've got 100 and that's 4, etc. Be aware that expedite forwarding is 46, and that best effort is going to be 0, and that it's a good thing just to review this table to make sure you're aware of it, but I wouldn't spend the time to memorize it there. So moving over to what actions we can take when we are have now marked and are taking in our traffic, what can we do with it? Well, we can shape it or police it generally. That this is the first type of action we can take. That with policing, as I said, this is just dropping our traffic that's going above our specified bandwidth. That this dotted line here is representing the maximum bandwidth allowed for that traffic flow, and that these peaks here are going above that specified amount. So when we police the traffic, we're just dropping anything that's over that specified amount. Now, if it's coming in too fast, the offending traffic is going to be dropped. Whereas when we shape it, as we see here, some parts are going above the specified throughput and others are below it. And that when we went above it, these end up equaling out pretty well, such that we are just releasing our traffic onto the line only at our maximum throughput, and that it is queuing up this amount here, and it's queuing up this amount here, and it's queuing up this amount here, and it's releasing this here. Such that this is now released onto the line. This is now released onto the line at our specified throughput, and that this queued bit here is probably being released onto the line here, so that we're staying at our specified throughput here. And that when it comes back down here, we'll probably see this here start to come back down because our inbound traffic flow is slowing down. And this is generally if it's faster than the interface can support, or it can also be if you are defining the amount of throughput. Say you have your voice traffic, your VoIP traffic, and that you want to make sure that it is set with your DSCP EF, your expedited forwarding. Make sure your voice traffic can get through, but you only want to give it 2 megabits. Because your voice traffic does not use that much throughput, and you only have 10 employees. There's no way you're going to be using more than 2 megabits, and in fact that is even pretty high just for voice traffic. And you want to make sure, in the event some bad actor comes into your network, say somebody comes in and places their computer on one of the desks, and that they are not an employee and they're a hacker, and that they start just throttling EF marked traffic into your network at 100 megabits, that they could now just hose your network and make it so that you can't get any internet traffic out because you are prioritizing this dummy traffic, this bad traffic, over everything else, and now nothing is working as expected. That you want to make sure that voice traffic cannot possibly just hose your network like that, so you limit it to 2 megabits, so that this guy who came in, who's marking all of his traffic at EF, he can only ever end up getting 2 megabits. All of your voice calls might start failing because he's throttling a bunch of dummy traffic onto the network. However, it's going to be okay that your mission critical applications and the rest of your network will continue working all right because you have limited your voice traffic to that amount. Now, as far as scheduling and queuing goes, that there's a few different queuing methods out there. That queuing and scheduling, allow for bandwidth limiting of specific traffic flows. And that, several methods do exist for allowing a single queue or multiple queues. That we can have many different queues, each even with their own priorities. As I said, you can apply a bandwidth limit to a specific queue or even a specific type of traffic. That generally that's done here with class-based weighted fair queuing. That also LLQ, this is low latency queuing. WFQ is weighted fair queuing. PQ is priority queuing, and FIFO or FIFO is first in, first out. So first in, first out, of course, that just makes sense. That's first traffic that comes in is the first traffic that gets sent out. Priority queuing and weighted fair queuing, these act very similarly. Whereas with class-based weighted fair queuing, this is where it allows you to configure several different queues and with your classes. That this is really what the modular QoS CLI is doing is that you are taking your classes of traffic. You're creating a class map. You're identifying your traffic and creating a class map to classify that traffic. And then you are applying a service policy to it to allow for weighted fair queuing so that you can weight certain traffic flows higher than others to give them a higher priority. You can give them bandwidth limits or even percentage limits of the bandwidth available. Say that you want it as a more dynamic kind of thing, such that based on which direction it's taking, say that you have a very dynamic routing protocol in your environment and that it could be taking different directions and that you have different bandwidths available. Say you have your router here and you've got 3 different ways that it could potentially go to get to this other section of your network. That this guy is a 100 megabit line, and then this guy's a 1 gig line, and then this guy's a 10 gig line. That you could just assign percentages of your bandwidth available to your various priorities or to your various classes of traffic, so that you don't end up with problems if you end up using a different line here, the 1 gig as opposed to the 10 gig. That if I specify I want to give 2 gigabits to my transactional database traffic, then, well, I'm running into problems with my 1 gig line because that transactional database traffic now has the ability to use the entire bandwidth of the line, and that you could cause problems in the event there's a problem there where it is throttling too quickly and that you're getting too much of that traffic there. Low latency queuing, this is also one I would be aware of, is that low latency queuing, it works a lot like priority queuing, but also creates a separate queue for voice traffic, and that low latency queue is emptied first. That it makes sure that your voice traffic is released onto the line first, always. And that after that queue is emptied, then your other queues start being emptied as well. That this figure here gives kind of a sense of what the queuing is like, right? Is that you've got your different traffic flows here. These could be, your YouTube traffic or your general internet traffic, your voice traffic, your video traffic, your traffic from your backup server, your traffic from your security cameras, so on. And then you are classifying that traffic and placing them into various queues here. And you're giving these queues different priority, such that the high priority ends up being put out onto the line first or more often. That your middle priority is second or a little less often, and that your lowest is whatever's left over. Or you could guarantee a certain amount of bandwidth, maybe just 1 megabit is going to your lowest priority, and that you can go ahead and send that out onto the line first. And then, last, or whatever is available. That it's important to keep in mind that all of this is per hop, right? That the queuing and the releasing of the traffic onto the line and at what bandwidth, that this is what's happening at the individual router level, that this doesn't necessarily impact how the upstream router or downstream router will be handling your traffic, that the QoS and the scheduling and the queuing needs to be configured at the per hop level here. You can classify and mark your traffic once and use that marking throughout your network, which is also where the trust boundary comes in as far as who you're going to trust, what devices you're going to trust for marking your traffic. And that you may want to discard any marking on your traffic. That say you've got your workstation here and you've got your phone. Excuse my poor drawing of a phone. And you've got your phone, that your phone, your computer here is connected to your phone, and your phone's connected over to your switch. And then your switch is connected to your router connected to your firewall. We'll just get put on fire, and that's over connected to the internet. Let's say your phone is marking its own traffic. And let's say this is a layer 3 switch, right? And that your phone is marking its own traffic as expedited forwarding, but let's say at your switch, you don't want to trust that marking. You can just choose to take that EF marking and rip it off of there and apply your own marking onto that traffic. That you want to take your trust boundary that was right here and you want to bring that up and put it right here and make it so that you don't trust this to mark its own traffic at all. But maybe you do want to trust it. Take some of that load off of your switch that's here and go ahead and allow your phone to mark its own traffic and move your trust boundary here, such that maybe you want to make sure that any traffic that's on your data VLAN that's coming from your workstation here, that you want to make sure you remove any marking that's there and that you don't want to trust that traffic. But perhaps you do, and you want to move your trust boundary out here and just trust everything. I wouldn't recommend it, but hey, it's possible. Maybe your environment calls for that. Anyway, thanks so much for going through this with me here. Just like the others, let's run through a couple of practice questions before we end off. First up, what DSCP value is recommended for voice? I did go ahead and put the table here just to make sure that you have this available. And this was looking at the decimal representation of DSCP, and that the recommended value for voice, we did say, is EF expedited forwarding. That has a DSCP value of 46. The answer here is C, 46. And finally, when there is no congestion, how is traffic released onto the line from the hardware queue? Now, I mentioned this just a couple of times, is that when there's no congestion, your hardware queue generally works in a first in, first out manner, that it will release it out as fast as it is able to, that the line allows, because there's no congestion, and that it'll just put it out there first in, first out. The answer here is A. I hope that this has been informative for you, and I'd like to thank you for viewing. Secure Shell Management Configuration. A lot of times we are managing our network devices, and generally you will SSH into them. If they are Cisco iOS devices, that's likely how you'll be managing them. And you may telnet, but if you have the option to use SSH, you absolutely should. That encrypts your communication from start to end. Even the username and password that you log into your device with, that will end up being encrypted through your secure shell. That with Telnet, all of your information is sent in clear text and is not encrypted whatsoever, and that is very susceptible to attack if somebody has access to the line between your management server, wherever you're connecting to your device from, and your device. That they're listening in on that and taking a capture, then they can see very plainly the credentials you're using to log into your device and any configuration that you're doing through Telnet. So Secure Shell, or SSH, is the preferred method of management for our devices. And a lot of us already know how to do SSH. You're going to use your terminal emulator like PuTTY or Secure CRT, something like that, and to go ahead and connect with SSH, and it just works. But if you pull a new device out of the box, or you're doing a write erase and need to go ahead and set it up for Secure Shell again, there are a few steps that need to be taken. So we're going to go through that in this video, and we're going to configure our devices for that, both as a SSH server and an SSH client, and show how that's set up here. First up, let's talk just a little bit about SSH. It is defined in RFC 4254. There were two versions developed, SSH version 1 and version 2. Version 1 is generally considered outdated now and is deprecated, that you should always use version 2 if possible. But a lot of our terminal emulator programs will just throw an error saying it's using version 1 and you want to continue, or you might have to explicitly add to allow connecting to version 1 SSH devices. It uses cryptographic keys for encrypted communication. And what does this really mean? Well, using public key infrastructure, not really public key infrastructure, but using public-private key of non-symmetrical encryption, that you can encrypt communications using a device's public key, and it can only be decrypted using the private key that is not symmetrical. If you try and obtain the public key, it doesn't matter. You cannot decrypt the communication that was encrypted with it. And that's actually something we end up doing during our configuration here, is that we are generating our public and private keys on our device for usage. That here I wanted to go ahead and show what setting up a SSH session looks like. There's a little bit of extra TCP traffic in there that is related to the SSH session here. However, that may just be some extra traffic that was generated by the device, that we just have a few extra acknowledgement packets here that may not have been needed necessarily, that sometimes the devices in GNS3 go ahead and just act a little bit wonky here or there. And it's just something to be aware of. That it does operate over TCP port 22. By default. So we see here that our client is 10.122 and our server is 10.123, that we are sending our SYN over to port 22 and getting our TCP connection started. And the way this ends up working is that we are negotiating our version of the protocol that we're able to use. We're saying 1.99 and 2.0 for the server. And then we're exchanging our keys. We are initiating the exchange of our keys. We're using Diffie-Hellman to actually exchange our cryptographic keys. The Diffie-Hellman allows for the independent creation of key material to be able to securely exchange information before you actually have a secure tunnel built. That it is a little less secure than using your cryptographic keys, which is why we are building that tunnel to allow for the more secure exchange of our keys. And then we are going ahead and actually exchanging our keys. And then we are sending encrypted packets to each other. And there we go. We have our secure lane set up, and that we are now exchanging encrypted packets, and each side is decrypting that when they receive it. And that's what it ends up looking like here, is that, you know, we're negotiating our protocol level, we're exchanging our keys, and boom, we're agreeing to go ahead and encrypt and decrypt our packets that are received during this session. So just going into that a little more here, is that our client initiates the connection by connecting to the server, you know, setting up our TCP connection, doing our SYN, SYNAC, ACK, and then the server sends over the public key. Now, this is a little simplified from our Wireshark capture there. We negotiate the parameters and open the secure channel, and then we go ahead and log in. And that's just this number 4 here. This is an encrypted packet that we can't see that during our capture. It just shows as encrypted data. In order to use SSH, you do need a iOS image that supports cryptographic features. These are the K9 images, that when you see in your image name, if it has K9 at the end, that is an image that supports cryptographic functions. If it does not, then you do not have an image that will support cryptographic functions. You will not be able to generate your RSA keys at all in order to use SSH. That if you ever run into a situation where you type in the commands crypto and it just says unknown command, then that's likely what's going on here, is that you do not have an image that supports cryptographic features. Just as a note here, this is not needed for the exam. SSH version 1 was supported as of iOS 12.0.5, and SSH version 2 as of 12.1 release 19, and that's on most platforms. There are some that were released a little later in the 12.1, but that's no issue here. That if you have like 12.0, which is very, very old, or previous versions of iOS, then you won't be able to support SSH and use that here. In the configuration, it does require a domain name to be configured. That when you go to generate your RSA keys, your cryptographic keys, if you don't have a domain name configured, it's going to throw an error at you saying that no domain name is configured. And we'll go through that in our configuration lab briefly here. And it is possible to use certificate-based authentication for mutual authentication with the client and server. That right now we're just doing key exchange for setting up our secure shell here, and then we're using username and password to log into the device. But it is possible to set up identity certificates on each side that are signed by some trusted certificate authority, so that you can mutually authenticate the two. The server can know that the client is allowed to connect by using the certificate, and the client knows that the server is actually who it says it is because it's signed by some trusted certificate authority. Awesome. So that's the brief overview of SSH. Let's go ahead and take a look at our lab here and the steps that we're going to take with that. So not all of the steps are needed for the client configuration. That in order to use SSH client, we need to go ahead and generate our RSA keys, and in order to do that, we have to set an IP domain name. Now we can go ahead and just leave the default host name of router, but there does need to be a host name there, that these are used in your key. That's why we need a domain name, is because that's used in your cryptographic key in order to go ahead and generate that. On the server side, we're going to go ahead and configure a local username and password. We're going to do something simple, just like Cisco. And then we also need to set the VTY line authentication method. We need to tell it login local so that we can actually log in with the VTY line. And down here, this is what our lab setup is going to be. We've got our SSH client over on R1 and SSH server over on R2. And following with our convention, it's 10.1.2.0/24 is the network between them. R1 is .1, R2 is .2. Now I have gone ahead and set up these IP addresses already. And I've set the host names, but that is all. Then we need to go ahead and set our domain name, generate our keys, set up our username and password on the server side, and set the VTY line authentication method. And then we're going to go ahead and log in from R1 to R2. We're going to SSH over there and take a look at what that is like here. So let's jump on over to R1 first and set up our keys real fast. So we're just going to pull open R1. We'll go enable. And first, real fast, let's do a show IP interface brief. My apologies. The IP address was previously set by DHCP from a previous lab and has not been set on our interface here. So let's go ahead and set that. It's going to be 10.1.2.1. And it's a /24. So let's go config T. Let's go to interface fast00. Do IP address 10.1.2.1, and it's a 24-bit. And there we go. And just to make sure, let's do a do ping 10.1.2.2. Make sure that R2 is pingable here. Yes, it is. Excellent. We do have connectivity. So let's go ahead and generate our keys. Let's go exit. And let's set an IP domain name. We got IP domain name, and this is going to be benjtrain.lab. Excellent. We already have our host name configured here of R1. So our full host name, the fully qualified domain name of our host here, is going to be r1.benjtrain.lab. That doesn't actually apply anywhere because we don't have that set up in DNS at all. It's just going to be used in our key generation. So in order to generate your keys, you do crypto key generate RSA. And actually, you can take a look at that here. We only have the option for RSA on this image here. And then we can use the general keys. That's what we want to end up doing. We do have the option of making it exportable. That if you don't set that, then the private key, so you know the key here is a public key and a private key, that anything encrypted with your public key can only be decrypted with your private key. If you do not set it to be exportable, you will never be able to see your private key. It is hidden away in iOS in such a manner that you cannot get to it. So we can go ahead and do general keys. We don't need to be able to export that at all. So we'll go ahead and just press enter. and it's going to ask us how many bits in the modulus. This is how long your key is. Choosing a modulus greater than 512 may take a few minutes, and it's going to be fine on this platform here that I went ahead and generated this earlier. It only takes a few moments, seconds at most, and generally you'll want to do 1024 or higher. Most modern terminal emulation software will throw an error if you're using a key length that is too short. That 1024 or higher is generally accepted as best practice. So we'll go ahead and do 1024, and there we go. It's created as non-exportable, and we actually get a log message here saying that SSH is now enabled. Great, we have our key available and SSH is enabled. Let's go ahead and do exit, and we can do, let's go end, and we can do a show crypto key, my pub key, RSA. And we can actually take a look at our key here. That we've got r1.benjtrain.lab, our general purpose key here, and that we also have our server key. Now it generates two separate keys here, and these keys you would expect, right? If you do a show run, these keys do not appear in our show run at all. That some devices will actually show your cryptographic keys in your running config. In this platform it will not, and in most of them it will not. You actually need to do that show crypto key command in order to see those. Awesome. So we've got the client set up here. Let's run on over to R2 and we'll get the server set up. So we'll do the same thing of generating our RSA keys, and then we'll set up our username and password and set the authentication method on the VTY lines. So let's go enable. Set config t, do IP domain name, I'll do benjtrain.lab, awesome, and then we'll do crypto key generate RSA general keys. I'll do 1024 as our key length. Excellent, so that's generated. So let's go ahead and create a username. We're just going to call it Cisco. Password, actually, you shouldn't use password. You should use secret instead. That secret will encrypt in a very weak encryption, but it will encrypt your password in the running config, so it's much more difficult for somebody to do an over-the-shoulder attack, right? Where they're just standing behind your shoulder and looking at your running config, and you end up scrolling by your username and password and they see the password right there. It'll make it much more difficult for that. So we're just going to set the password as Cisco here, and there we go. Awesome. So then let's go to line VTY 0 through 4. We're going to do login local. Excellent. Let's go end. Great, so now we can run back over to R1 here. We can try to SSH and log in to R2. So that command is just SSH, and we specify what the username is with the -L using the Cisco username that we just created. And then the IP address here is 10.1.2.2 for R2. We're prompted with a password here. This means that we have negotiated our SSH tunnel here already, that the encrypted communication is now set up, and it has accepted that session, and that we are now trying to log in with our password. If I just type in Cisco here as the password, we're now presented with our prompt here for R2, and we are now in R2. Now I'm trying to enable here, but there is no enable password set, so it's not allowing us to do that. But we have now successfully set up SSH on our device and connected to it from another device as well that was set up as an SSH client. Awesome. Just like the other videos here, let's run through a couple of practice questions before we end off. First up, what attribute must be configured by the admin before generating RSA keys used for SSH? Is it the interface name, the username, the domain name, or host name? So the host name is something that is needed, but that can just be left as the default router or switch host name that's on your device. So that's no problem. That the attribute that must be configured by the admin is C, the host name. In the event you try to create your RSA keys without setting a domain name, it'll throw an error for you saying there is no domain name set, and that you'll need to go back and do that real quick. So finally, is the below iOS image capable of connecting via SSH version 2? And it's a show version output here for the 7200 router using the Advanced Enterprise K9-M, and it's version 12.4. So we did mention that SSH version 2 was released in 12.1, so that's fine for our version here, and we have the K9 here on the end of our image name. So yes, this does have the cryptographic functions built in. So the answer here is yes, this is capable. I hope that this has been informative for you, and I would like to thank you for viewing. FTP and TFTP. At some point during your network engineering career and in working with these devices, you will run into the situation where you need to either transfer files to a device or off of a device, to back up the configuration to some external location, or to go ahead and update the firmware and transfer a new iOS image over to the device. This is going to happen, and Cisco wants to make sure that you understand what's used generally in order to do this. And FTP and TFTP are generally the protocols of choice when looking to do these file transfers. And most commonly, you're going to end up doing this for software updates, to go ahead and transfer a new iOS image over to the device, but there are also other uses, and we'll cover a little bit of those in just a few slides here. First up, let's talk about File Transfer Protocol, FTP. So, specifically the exam topic on the CCNA here, that it says to go over the function and use of FTP and TFTP in the network, and that we need to describe the capabilities as well. So, File Transfer Protocol here, it establishes two separate TCP connections for control and data transfer. What it actually does is it operates over TCP/21 for control messages. So the client sends a start command over to the server over TCP/21 here, and then the server responds to the client with a port number. So then this is in passive mode though, right? Is that FTP has either active or passive mode, where passive mode is where the client connects to the server for the data, but the active mode is where the server actually connects to the client. The server initiates that connection. And think about it, right? That doesn't work well with firewalls or NAT, of course, either, because the server is trying to initiate a connection inbound. And during active mode, the inbound port number for the client, it ends up being just an ephemeral port number. It's random. It is among a range, but you can't really specify every time what that port number is going to be, so it just doesn't work for having a firewall. So this is why passive mode was developed. And mind you, this was made back in RFC 1579, and then that's where passive mode was introduced. This is back in the 80s, right? When firewalls were not necessarily so ubiquitous. So they were starting to be up and coming and be in most networks. So that's why passive mode was brought in to play here, and there was a standard defined for it. So like I said, the server responds to this port 21 communication, right, giving a port number back, saying, hey, go ahead and open up a connection on this port number for that data transfer. So then with the passive mode, the client starts the connection to the random server data port. That is not necessarily true. It does default to TCP/20 for data, but that is a configurable item and is not necessarily true all the time here. That can just be a random server port for the data. And then, in response, the server will send the data back, or the client will send data to it. That is a full interactive file transfer session that is two-way file transfer. You can upload, you can download. The server could request files from the client, and the client can request files from the server. FTP does not provide any encryption. So that includes your authentication. Is that generally there is authentication for FTP. There is defined standard for having anonymous authentication so that there is no username or password exchanged, but it does not encrypt that communication at all. So that is going to be sent in plain text. So you might want to consider that it doesn't actually secure its own communication here. So the underlying line there, the management line that's happening between the two, should be secured because the protocol itself does not provide that. So that's how file transfer protocol works. And you probably touched on FTP before, maybe used an FTP server like FileZilla or something like that to go ahead and upload documents to a web server or something along those lines. It's pretty intuitive, right? But something not everybody has used is the trivial file transfer protocol, and that is TFTP. So TFTP is a really, really lightweight file transfer protocol. Its most recent definition was in RFC 1350. It is a connectionless protocol using UDP 69. It does not care to actually provide reliability in the underlying transport protocol. This is why we have acknowledgments that it is providing some reliability in the actual TFTP in the protocol itself rather than in the underlying transport protocol. It's a very simple design. It requires a really small amount of memory, which is why it's ideal for network booting, is that in your pre-execution environment, right, as your device is booting up, that we only have to load this very small software into memory in order to run TFTP, that it's very lightweight. And that makes it really great for loading into your pre-execution environment and being able to boot from the network. Now, Cisco devices, you can configure FTP for network booting, to where during boot up it will reach out to some FTP server and grab an iOS image and boot from that image. They'll get that image, it'll decompress it, and boom, it'll go ahead and boot from it. But TFTP is usually the protocol of choice for that, just because of its simplicity and ease of use. It is only for unidirectional transfers that the client must initiate either a read or a write. It can either obtain data from the server or put data on the server, but the server cannot request data from the client. That it's one way here. And for each session, it is only one way, that you either request a file and then that session is over, or you put a file and that session is over. Just like FTP, there's no encryption, but with TFTP, there's actually no inherent security whatsoever. It does not authenticate anything. It doesn't provide any mechanism for that. You cannot provide a username or password because that's just not built into TFTP. But that's no problem generally for our uses here. If you just need to quickly take a backup of your configuration on your device, it's really easy to go ahead and just stand up a TFTP server. There's, applications out there for Windows, Linux, Mac, and just go ahead and stand it up real quick, point your client, your router or switch or whatever device over to that TFTP server, and boom, just send your file over. It's quick, it's dirty, it's easy, it's going to be nice and fast. But same for network booting. If you have your management network secured, then this is a nice option for network booting as well, as long as you don't really care about the authentication mechanism not being there. But of course, you could use FTP instead if you do wish to go that direction. So as far as the uses here for FTP and TFTP, right, is that I did touch on that a little bit, is that it's used for transferring configurations, your running or your startup, from or to your device. You can back up your configurations. You can restore your configurations to your device. That I can go ahead and transfer a running configuration to my device. I can copy from a TFTP server, and instead of Flash here, you can do the option of running config. And that will go ahead and restore a configuration directly into the running configuration of your device. Or same deal, I could put here to startup config. And that we can go ahead and restore our configuration directly to our startup configuration, or vice versa. Go ahead and do startup config here and have this, instead of Flash, be to an FTP server. And go ahead and back up our configuration. And similarly, that's how you would do it for your iOS image as well, that we use the copy command here when you're actually in your server, you're actually in your device, that through ROM-on mode, or ROM-on, you can go ahead and configure network booting to have it reach out to some FTP or TFTP server to boot directly from an image stored on that server. And you can back up or update your system image files, as I said, your iOS images, or on ASA, your ASDM image, or your ASA software, that you can go ahead and transfer that around. It's just generic file transfer, right? And that your log files, sometimes you configure your device for having crash logs or other various logs that are not necessarily easily moved off of the device, like syslogs, where you can just export that to some syslog collector. You can go ahead and just do a copy and do the file, copy Flash, and the syntax here is going to be, like Flash : / and then your file name here, right? So that we can do, backup log. And that, copy that over to our TFTP. And that's how you would transfer that that file off of your device and onto your file server, your TFTP or FTP server. Now, I know that this video here has been pretty quick. It's just a quick and dirty rundown of FTP and TFTP and where you would use that, and their fundamental protocol bits here. That the things to really remember, UDP 69 for trivial file transfer, that is a connectionless protocol, and that there is no authentication, and that there's no inherent security there. And same thing for FTP, it operates over TCP 21. For the control messages. You don't necessarily need to know that's 20 for data, because that is not necessarily a set port number there. That the only time this would ever really come up is 21 for control messages, and that it does not provide any encryption. That for that you would need SFTP or FTPS. Which we're not covering that at the moment here, just because that's not gone over in the CCNA exam topics. So just like the others, let's run through a couple of practice questions here before we end off. Over what port are FTP control messages sent? Now, I know I just mentioned this here, but I did want to just drill it down one more time, that this is a connection-based transport protocol, and by transport protocol, I mean TCP. And that it is TCP 21 for the control messages. The answer here would be C. And finally, does TFTP use a connection-based or connectionless protocol for its transport? And remember, our transport protocols are our layer 3 protocols. Our layer 4 protocols for TCP, UDP, etc. That this is going to be a connectionless protocol because it is operating over UDP. Our answer is A. Now, I hope that this has been informative for you, and I'd like to thank you for viewing. Security concepts. A lot of the basics in cybersecurity honestly revolves around vocabulary and having definitions for things and understanding what exactly they actually mean. And this allows you to have a more intelligent conversation with your peers and other people in the field when you understand what they actually mean when they say that this is a threat, or that they've patched certain vulnerabilities, or they found malware utilizing an exploit. That what we'll go through in this video is some of these terms and what they actually mean and how they're relevant. These concepts of a threat, a vulnerability, an exploit, and mitigation, and how that applies to cybersecurity. So first up, let's talk about a threat. So a threat is anything that has the potential to cause harm to computer systems. That's a really broad definition. Think about how wide that is. That could be everything from a power surge all the way to natural disasters to software bugs or vulnerabilities to legitimate manufacturer defects, that these are all threats to your computer systems as they could cause harm. Now, the thing that we're going to be talking about mostly is malware. So malware is malicious software. Malware are viruses, trojans, those are threats, and they have the potential for an attack that hackers out there can use these, and the potential for that attack, that is also a threat. The hackers being out there and having the ability to do this, that's a threat. And threats are what we work to mitigate or to lessen, that we're trying to reduce or remove these threats entirely. And that over here, this graph shows a little bit about the threat landscape, right? That beware of the social engineer, that your threats don't all have to be digital. They can be of your employees, and having a good security program and user awareness in your organization and training can help reduce this threat. And ransomware, it poses a grave risk to availability, that this is a threat and has a very large risk towards availability specifically of your data. That ransomware, the way ransomware works is it goes through and encrypts your data and it holds it ransom. That typically the hackers will be requesting some amount of dollars or Bitcoin or what have you, a currency, in exchange for the encryption keys to decrypt all of your data. And the greatest threat may come from within, that, having a disgruntled employee, that can be one of the most dangerous things for an organization. Just because they have the access, they are usually unsuspected, and that they can go ahead and cause great damage, and even sometimes remove their tracks from causing that damage, really creating a problem for you in trying to figure out how this was done and being able to patch this so it doesn't happen again later. And as we just talked about, that malware is a huge threat. That ransomware is a type of malware. And that malware in general, software, although we're getting really good at defending against malware, at identifying software that poses a threat, and being able to identify that and take it out of the equation here, either block it or remove it, that although these still do pose a significant threat, we're getting really good at identifying and mitigating that threat. And denial of service attacks, that fundamentally the way the internet works can cause denial of service attacks, that it opens up that vulnerability or attack vector for organizations out there, and there are certain steps you could take to mitigate that threat. But this is like sending a SYN flood to your web server, where you're opening up all these half-open connections. You're sending a bunch of SYNs, and your server is sending back all of your SYN-ACK, right? And your TCP three-way handshake here, and they're sending back all these SYN-ACKs, and they're opening up this port, right? Because it has to have that connection open on the server and available to receive your ACK in response to go ahead and complete that three-way handshake. And if you're sending thousands, hundreds of thousands, millions of these SYNs over to your web server, you can tie up all of the available resources of all of the available web servers and make it so that legitimate traffic has a very hard time getting through. And that size really doesn't matter. That oftentimes the way hackers are operating in reality is that they are scanning the internet and looking for available vulnerabilities that are known, to go ahead and try and apply an exploit and see if they're able to exploit these vulnerabilities. And because of that, it really doesn't matter the size of your organization. If you have vulnerabilities in you, or fundamental to your organization or to the hardware or software that you're using, you are at risk here. That although there are targeted attacks, of course, in general, you're still at risk. Size really just doesn't matter. You can't say, well, I'm too small, I'm not at risk. That's not real. That's not a good argument here. And that in reality, we are slow to detect and respond to threats. That it's a little difficult in reality, threats are hard to identify, because if you have a hacker that's compromised your system, that's actually pretty difficult to differentiate that between legitimate traffic that's going on, unless you have malware coming through. But if you just have unauthorized access, somebody that is accessing the administrative console of your devices that shouldn't be, identifying that unauthorized access as opposed to having authorized access, especially when they have compromised or taken without authorization the credentials for an authorized user, such that it looks like that the authorized user is the one who has gained access to this device or software, but that it is an unauthorized person that's taking advantage of that or using that. That is extremely difficult to be able to track down and identify. And that the biggest threats aren't generally found in the headlines, that when you're reading about the large ransomware attacks and things of that sort, there are hundreds and thousands more going on that are not reported, either because they are confidential or they are kept secret by the FBI or government organizations, and that they are not widely publicized. And so then we need to be aware and stay on top of security best practice in order to make sure that we are limiting our vulnerabilities as best we can to reduce the potential risk of these threats, to try and mitigate the threats as best we can. So a vulnerability, I've stated this a few times here, that a vulnerability is used to cause harm or provide unauthorized access. That typically, a vulnerability describes a software or hardware bug which can be exploited. That an exploit, we'll get to that in the next slide here, that it's the actual command or software that causes unanticipated or unintended behavior. And that vulnerabilities don't just have to be software and hardware. Don't just have to be software. It doesn't have to be logical. It can be physical vulnerability. That your locks are vulnerable to a certain type of lockpick, or managerial vulnerabilities, policy-based vulnerabilities within your organization to allow for social engineering to be able to take place easily. That in the event one individual person, your front desk coordinator, becomes compromised, some social engineer asks them for information that they should not be giving out, that in the event that person proceeds with that your policies may allow for that person to then gain a lot of access within your organization just because one person made a bit of a mistake, and one that might not even seem that terrible at the time, that might seem pretty trivial. So that's what a vulnerability is it's anything in your organization that can be used to cause harm or provide unauthorized access. And then exploit, I mentioned this a handful of times, that people use exploits to take advantage of vulnerabilities, that they exploit the vulnerability, and that they use this to gain access or cause harm in some way through unintended or unanticipated behavior. And that attackers, they pose a threat by leveraging vulnerabilities with exploits for malicious activity. That's a pretty dense sentence there that uses our vocabulary that we've just learned here and really puts that into context as to what each of these individual items means. And that exploits are generally used to deliver malware to a device, that you use an exploit to deliver malware. The ability to run malicious code arbitrarily, or that's like what a buffer overflow exploit is, where you are putting too much information into a buffer and it overflows, and then arbitrary code is allowed to run on your device, that you are allowed to run malware or to deliver malware to the device through that buffer overflow. And that's what an exploit actually is it's the thing that allows unanticipated or unintended behavior to happen, and that's generally used to deliver malware to a device. Now, as far as mitigation, specifically, I wanted to take a look at the dictionary definition of mitigate, because I know a lot of people have used this word and that you might not really know exactly what the definition is, that it really means to make less severe, serious, or painful, to lessen the gravity of. That it's to make it less severe. That I'm sure makes sense here, that when we say we're mitigating threats, we are making these threats less severe or less serious. And it's not saying to eliminate. That's not what mitigate means. It means to lessen the severity of it. That the threats may still be there. They may still pose a threat, but you've done your best to mitigate them, to lessen the severity of them, to make them less painful for your organization. And that some mitigation techniques are threat prevention, to prevent the threats from ever occurring, to have best practices and policies that protect your organization, and threat identification, to know what the threats are that are out there through the use of security tools and management to identify the active threats that are out there. That the things you don't know are out there will cause some of the greatest problem, that you may not know whether you're secure against them or whether they have occurred or not. And threat remedy, to the strategies and tools to reduce the impact of an active attack. So to remedy a threat, something that has already posed problem, to have an active attack, and that the strategies and tools you use to reduce the impact of that. That is also a mitigation, to make it less painful and to make the attack less serious or less severe through threat remedy, which is a mitigation technique. Now, thanks so much for going through this with me here. I know this is a pretty short one, but just like the others, let's run through a couple of practice questions before we end off. First up, which option best describes malware? Is it an exploit, a vulnerability, a threat, or a mitigation technique? Now, malware is usually delivered by an exploit, and an exploit takes advantage of a vulnerability. Malware is something that causes problems. Mitigation techniques are ones that reduce the severity of problems. So the answer here would be C. It is a threat. And finally, mitigation techniques are used to lessen the impact or chance of being impacted by what? By malware, vulnerability, exploit, or threat. And that, like I just said, is that typically exploits use a vulnerability to deliver malware, and that malware is a threat. So the answer here would be A. Mitigation techniques are used to lessen the impact of or chance of being impacted by a threat. Now, I hope that this has been informative for you, and I'd like to thank you for viewing. Elements of a security program. In this video, you're going to get a little break from the hard technical information because this information that we're covering is really high-level overview of an organizational security program. The elements of a organizational security program that you should be aware of that you can implement in your organization to help enhance the security within your organization. That a lot of your risk comes from your end users, and making them more aware and training them in how to identify potential threats and how to avoid them, how to handle them, can be one of the cheapest actions that you can take as far as security is concerned within your organization, and also have the greatest reward. So this video is going to be a little short. We're going to run through these elements here and take a look at what they actually mean and go from there. So first up, an overview of a security program. So technical security measures such as your firewall and your login credentials and having out-of-band management to your devices, that these are really just a single part of your organization's security program. Down here, we see that at the base of our security program, we have policies and procedures. And then above that, we have user awareness training. These are really the foundation of your security program. That if you don't have proper policies and procedures within your organization, you can really be putting yourself at a high risk or higher risk. And that lack of user awareness of the potential threats out there and effective policies, they put your business at risk. That your users need to be aware of the fact that they might get spam, or they might get phishing emails, that when they go to websites or their banking website, or if they get a withdrawal request from their boss and it seems a little out of ordinary, then they should double check on this and make sure that this is actually correct. Now, I have seen circumstances where this happens, where the CEO's or a controller's email gets hacked and the hacker has control of this and sends a withdrawal request, and then they wait for the response of saying, are you sure you want to do this? This sounds a little out of ordinary. And then they go ahead and reply, yes, I want to do this. And that your users need to be aware that this is a potential problem. This is a potential threat out there, and that they should follow up with a phone call or an email to another person who has the ability to physically walk to that person and verify. Or you can use email encryption methods like SMIME to go ahead and verify that this is actually the person, that the hacker would have needed to take control of that workstation, to have access to that certificate to be able to send the encrypted email. And that the three parts of our security program here are awareness, training, and access control. And we're going to go through each of those momentarily here. And first up is user awareness. So awareness training provides really the greatest benefit at the least cost. That through just a few seminars with your end users, you can show them a lot of the potential risks and potential threats out there and what their risks are to the organization. That something I wanted to show here is that this has been around for a while, but used to be understood that when you don't have this little lock icon here, that you're not in a good place and that you need to go away. And that's not good advice anymore. That, as you can see, we are not at PayPal's website here, and we are being prompted to log in to PayPal. And that this is definitely a phishing website, and that we are secured by HTTPS. That all HTTPS does, or all the certificates generally do, are verify that you do indeed own the domain name, and that the domain name presented matches what is on the certificate here. And that's all it cares about. There are some certificate providers out there that do much more investigation into the actual business and make sure the business is legitimate and real, and they will check the website. And that exists, but there are not many of them. That generally revolves around the insurance that they provide with their certificates. And that security awareness is really about understanding the threats that exist and their risk. To understand that there are things such as phishing and social engineering, that when you receive a phone call and it's asking for some information, asking you to just do them a favor and maybe circumvent some policy or exploit some policy to provide more information than you would usually provide, or provide access that you may not generally provide, that this is something that exists, and that your end users should be aware that they need to be very cautious about providing information or access to their network, to their computers, or potentially useful information that they have, which I know that that's very broad and generic, potentially useful, but to help them have looking at things with a cautious eye, and to always raise their hand and check that when something doesn't seem quite right, that they should say something. And you know that classic United States, we have with the Department of Homeland Security, they have coined this term of see something, say something. And that's really what your end user should be doing. If they feel that they are seeing something that's a little out of the ordinary and a little weird, they should say something. That's something worth investigating, at least a bit. And that user awareness is increased through training. So user awareness is a part of your organization's security policy and posture here, but that it is increased by training your end users. And the types of threats, just to briefly go over this, that this can help mitigate are phishing threats, social engineering, and malware, that you can help prevent malware from coming onto your network by training end users a bit into into not going to unknown websites terribly often, unless they know what they're looking at. That in the event they get the certificate warning on their page here of saying this certificate is not valid, or that this website's domain doesn't match the certificate, don't continue to that website. And that if they start getting pop-ups saying that your computer's infected, click here, don't click there. And that if they run into problems, if their computer starts acting strange, turn it off. To make it so that you cannot continue spreading your virus around. That perhaps they suddenly got ransomware on their computer and their computer's acting very slow and a little strange, that they should go ahead and just turn it off. Contact IT, let them come over, turn it on when it's disconnected from the network, and see what's going on. There might be nothing, and all you did was waste one employee's time for a little while, and that IT ended up confirming that this was okay, rather than potentially there was ransomware and that you could have brought down a significant portion of the company because they didn't do anything. Now, as far as your training program goes, that training not only helps increase user awareness, but it helps enforce proper responses. So with your training, you are training your users into what the proper response is to some of these threats. That training can involve recognizing different types of phishing attempts, of just standard phishing through a website or through an email, vishing, voice phishing, that when they're calling over the phone pretending to be some other person or some other organization asking for credentials or getting you to provide access into their network. Smishing, which I know is a really fun sounding word, but that's phishing through SMS, through text message, of asking for credentials through that way, of saying you just received an access code, please provide this, or something along those lines. Or spear phishing. This is a common one out there, that spear phishing is when you're going after one particular person. Very typically is a high level person in that organization, the CTO, the CFO, the CEO, your high level executives at an organization, and trying to phish their credentials. That when you do that, you have a lot of power. You can get into their email and you can send emails out to the organization. You can probe a little bit and get more information. You can monitor their emails, their documents, and things of that sort, and see the types of words and phrases they use to go ahead and more effectively mount an attack. That this is something to be aware of, that many executives now are aware that they need to look at everything with a very cautious eye to make sure that they aren't being spearphished. And that you can identify social engineering attempts in person or through email or phone. The idea of providing somebody access when they really shouldn't have it. That somebody might walk in as dressed as a engineer for a fire protection company, requesting access to the server room to check out the fire protection systems that are in the server room, and that in reality they are a penetration tester, and that they just have a USB drive with them that they plug into the server, and that they have now deployed malware which is a rootkit and allows them backdoor access into that server. That this is a very real thing. That I've read several articles about that, where this is a real attempt from penetration testing companies and from actual hackers to go in person to an organization dressed as somebody of authority, of a engineer for their fire protection, or as a firefighter or a policeman, and that they don't actually have their credentials. You don't have anything on your calendar saying this is going to happen, and because of that, you need to check it out. That your end users need to know, your front desk person, your security needs to know that unless this is verified, that they should have access to this area, and that you have corroborated their story from elsewhere, then they should not have access. You need to say, I'm sorry, you're going to miss your appointment. I do apologize, but we need to verify this before we allow you access. And that training really needs to be followed with reinforcement through engagement. That you can train your end users, but if you don't engage them, then you don't know how well your training really took hold for them, and you have really little ability to track how your training program is going. That you can run internal security campaigns to test and track the training efficiency, or the training efficacy. That I've seen many times. There's a large business now around sending false phishing campaigns that you can go, and I know one of these companies is called KnowBe4, that you sign up with them and you go ahead and add in their IPs to your SPF records. If you're not aware of what that is, that's the Sender Protection Framework. That is a DNS record that says that certain IP addresses, public IPs, are allowed to send emails which show to be having a source domain or show to have a from domain of your domain. So you're allowing this company to send emails on your domain's behalf, and they're sending phishing emails, and they're fake phishing emails. They're not actually stealing your credentials and using them for malicious purposes, but they're sending out these phishing emails with a bunch of tracking information and code in there so you can know on an aggregate basis how many of your end users actually did go and log into PayPal or did go and log into Facebook from this email that was not quite right and was a phishing email. How well did your training actually take effect? So you have engaged them and you have tested them and you track them. And then that's how you end up getting your measurements to see how well that is actually taking effect here. Awesome. So then finally, let's go ahead and wrap up with access control. So access control, the standard procedure is to operate in a principle of least privilege. You'll see that abbreviated sometimes as POLP. That the principle of least privilege is that you should only have enough access to perform your specific job duties and no more. If you only need access to the help desk area, then you should not be given access to the server room as well. Or if you only need access to the financial documents, you should only be given access to that shared drive and not also to the marketing drive or to the technical drive with IT information in it. That it prevents low security level accounts from accessing more sensitive information. That any individual, in the event that their credentials are in some way compromised, that you can be sure that the only information that could be compromised is what that individual would need access to, is that level of staff member. Technologies like 802.1x can secure your internal network using device certificate authentication. The 802.1x, that is pictured here, where your device is the supplicant, your switch is the authenticator, and that it goes ahead and authenticates your access with the authentication server. This is actually really cool. If you're not familiar with it, I would suggest going and taking a look and perhaps labbing that up. That's not covered in the CCNA, but it allows you to connect through a hard wire into the network, and that the only information, the only data that's allowed between you and the switch is authentication information. No data is actually allowed, no traffic is actually allowed except for that authentication information until you are authenticated and allowed onto the network. Then it will open up that port and allow general traffic throughput. Here I wanted to just show some access control devices. That here we have a palm scanner or a hand scanner, that this goes ahead and takes a look at the blood vessels in your palm and treats that as a uniquely identifiable pattern, and that's how it's identifying a person. That, remember, that is authenticating. That is matching up your person to your identity, to your digital identity, and saying that yes, you are actually this person, and that you are then authorized to access the areas in which your position, your identity is allowed. And here, this is an example of a man trap. A man trap is like a vestibule area, a place where you're generally entering into a highly secure area. You go in, you authenticate yourself, it confirms authorization. In the event you are not authorized, you're trapped there. and that in the event you are not authenticated, you're trapped there. And then they can go ahead and check that out and make sure that you're not allowed to just run through into a secure area or potentially out of one either in the event you're trying to gain unauthorized access. Awesome. Now, I know that that's been a lot of just really non-technical information here, but just like the others, let's run through a couple of practice questions before we end off. So first up, what are the 3 parts to an organizational security program? Is it awareness, training, and testing? Training, testing, and tracking? Awareness, training, and access control? Or training, testing, and access control? Now, here we covered the 3 items of awareness, training, and access control. The answer is C. And then finally, what is the purpose of user awareness training? Is it to have staff understand and comply with corporate security policy? That is a good point, but not necessarily. To ensure staff are aware of consequences for violating security policy. That should be something that is included in your policy training. However, to help staff understand threats that exist and their risk to the company, or for compliance with government regulations, you may need a training program for compliance, but the overall purpose here is to help staff understand the threats that exist and their risk to the company. The answer here is C. I hope that this has been informative for you, and I'd like to thank you for viewing. AAA. Now, if you reside in the United States, you might recognize AAA as being the American Automotive Association. And of course, that is not what we're talking about here. The AAA in the context of cybersecurity and security in general stands for authentication, authorization, and accounting. It is the 3 A's around this concept of managing identities, what those identities are allowed to access, and then logging what they have accessed or attempted to access. So in this video, we're going to run through these concepts in a little more depth and take a look at what they actually mean and some examples. And then we're going to go through a lab with configuring privilege levels on a router and usernames with privilege levels and how we perform access control using local username and password database on the router in order to get some semblance of access control here. So first up, let's talk about authentication. So authentication is the process where you verify who you say you are, is that it is matching up a person with their identity, where identity is a little bit more of an abstract concept here of the identity that is stored in your server or in your database to match up the person who is accessing the resource here with their identity that was created in the system. Typically, this is done with a username and password. As you can imagine, you go to any website, you go log in with your email address or your username, and then you type in your password and you try to log in, and that authenticates you. That if you provide the correct single factor here, the correct password, then that will allow you to log in, and it matches up that username, that identity, with you, the person who is logging in. Now, passwords are highly susceptible to attack. Of course, as we know, we hear about this all over the place. People are getting their passwords brute forced, or they're being subject to phishing campaigns where maybe you are being directed to a lookalike page that looks a lot like Facebook, and that you end up typing in your username and password, but in reality it's not actually Facebook, and that you just gave your username and password to some third party. And there are other attacks that usernames and passwords are susceptible to, but there are certain policies that you can put into place to help reduce the risk of these attacks or the risk of these threats. That password complexity requirements requiring, uppercase, lowercase, numbers, special characters, and certain length, age, and history requirements saying that you must change your password every 30 days and that you cannot use the last 5 passwords that you have used, and secure password management using a secure password management software. A lot of people, they go ahead and write down their password on a post-it note. I have definitely personally seen before where somebody's written down their password and left it on a post-it note attached to their monitor.
And then all it takes is somebody walking by and a glance over at it, and there you go. Your password is now compromised, and you don't know who now has access to your account and can really cause some trouble. And to go a little further into this, that what's a lot more common now is rather than just using one factor like a password to verify your identity and to prove you are who you say you are, is that we're going in the direction of multi-factor authentication. That not only do you need to provide a password, but you also need to provide something else as well. And very common is, an SMS text message, that getting a text to your phone and typing in the code that it texted you, saying that if you have the ability to receive that text message, that if you have the SIM card for that phone number, or you have that cell phone, and also your password, that you must be who you say you are. Or a biometric scan. These are getting a lot more common. You see that a lot with cell phones now, as they have fingerprint readers on them, and to go ahead and use biometric scan to open up your phone, or also in corporate environments, retinal scans are really common. Or I've seen where they do hand scans. They very similar to how a retinal scan works, where it scans and looks at the unique blood vessel patterns on your retina, that similarly you have unique blood vessel patterns on the palm of your hand. And putting your hand down on a scanner, it can go ahead and take a picture of that and match that up. Now that is something that you have or something that you are. Or a certificate stored on a fob or USB. This is a lot like the brand YubiKey, if you've seen those before, where you're essentially providing a very, very long password, a certificate. And then not only that, but the certificate may be signed by some specific CA that the provider gave to you, that they gave that certificate. Perhaps you can do this with Gmail or other email providers as well, and then you must provide this certificate. Generally you store it on a USB, a thumb drive, and then you plug that in and it reads in that certificate to allow access. Or what's also very common in high security environments as well are time-based one-time passwords. You may have seen these before, where perhaps on your phone, or you have a little physical device, you have this little fob, right? This little thing, and it's got a little button here, and it's got a little screen on it, and that when you press the button down, you end up getting a sequence of numbers show up on your screen. Maybe it's like 6 numbers or 8 numbers long, and that number is good for 30 seconds or something along those lines, and you have to put that in to your application in order to log in. And that the physical ones are called hard tokens, and that you can typically do this as well with a software, that you have a software on your laptop or on your phone is much more common, where you open up your authenticator application and generate those numbers from your authenticator application, this time-based one-time password that you type in, and it's only good for 30 seconds or a minute, and then you have to put it in, and after that period of time, that has now expired, and that you would need to generate a new one. That this has been thought to be more secure than text message, that there are some carriers that easily allow your SIM to be transferred so that other people can be able to get access to your text messages and receive your phone calls. That this has been a more common attack recently, and that the time-based one-time passwords, this physical hard token or device, you need to physically have that you cannot call up some carrier and have them transfer you to a new time-based one-time password device or a new hard token or soft token. Now, of course, your internal policies at your help desk for reassigning a token would need to be sufficiently secure, and that's where policy management within your organization really comes into play, that you need to be very, very sure that the person who's calling into your help desk saying that my fob doesn't work anymore and that they need a new one assigned to them, you need to be very sure that that person is who they say they are, so that you're not just providing some attacker with a new soft token to go ahead and log into your very secure applications. So that's authentication, right? Is that you are proving that you are who you say you are. You are matching up your person with an identity. Now let's move on into authorization. The authorization is the verification that your identity is allowed to access certain resources. That authentication verifies you are who you say you are. Authorization asks, are you allowed to do that? And that often this is performed using permission levels or role-based access control. And on Cisco devices, TACACS Plus allows for per command authorization, so that when you set up TACACS Plus authorization on your device, each time you type in a command, show interface, show IPOSPF, or configure various commands, that each one of those commands, before your device actually processes it, it's sending an authorization request to the TACACS server asking, is this identity allowed to run this command? If you are not, then it will not allow you to do so, and it'll say that you don't have authorization for that. And that authorization, it determines what the identity is allowed to do. That's the difference between authentication and authorization, is that when you say you are not authorized, it's, well, you have apparently authenticated and they know your identity, and they know your identity is not allowed to do this. It is not authorized. But that authenticating is proving that you are an identity. And then lastly, moving on to accounting, the last A in our AAA. Accounting is just the record keeping of resources accessed by an identity. That it is the logging of things that your identity has done. And on a network device, it would be the commands run by an identity. Here we have a conversation with a TACACS Plus server and a client to take a quick look at what that looks like. That we have our authentication process happening here, where we try to connect, we send our username and password, and that we indicate a pass or fail as to whether you are authenticated or not. And then we move into the authorization as to whether you're even allowed to get into the device or not. Great, you've authenticated, I know who you are. Are you even allowed to connect to this? So we send that our service is shell, and that we indicate pass-fail status as to whether we are allowed to get to the shell or not, and get into exec mode, and indicate whether you are allowed to do that or not. And down here we have our accounting, that we have the accounting for commands. Here's the command I sent, and it is doing accounting for that, and then we get a response saying that it was received, confirming that we have logged this command and that it has been accounted for. And that's the last A in our AAA. So let's take a quick look here at access control and privilege levels on a Cisco device. I know this slide has a lot of text on it, but let's just run through it a little slow here. Is that usernames on Cisco iOS can be assigned privilege levels to adjust their level of access. You see that here, is that we created a username by the name of helpdesk, and that we assigned it the privilege level of 5. Now you may or may not know that there are 16 privilege levels on a Cisco device. It is 0 through 15. 0 is essentially not used. The default privilege level is privilege 1. So it's 1 through 15 that's actually used by default. Privilege level 15 is what enable mode by default sets you at. When you do enable and you type in your enable password, you are now at privilege level 15. Before you type in enable and you're just at the exec prompt, you are at privilege level 1. So specific commands can be allowed at certain privilege levels. By default, since you're going to privilege level 15, that is the top privilege level. All commands are allowed at privilege level 15. You are an administrator. You have the maximum amount of access. You can set the username privilege level, as I said, with the username, name of the username, privilege, and then the privilege level you want to apply to it. And mind you, the username must be created already, where you have username, name, and then the secret or the password, and give the password there. That you can also specify the privilege level inside that command by doing username, privilege, the number, and then also doing secret on the end here. and setting the password there. That you can do that all in one command. And that with the privilege command in configuration mode, you can set the privilege level of specific commands. So if we want to allow level 5, the privilege level 5, to access all show commands, we would use this command here, is privilege exec level 5 show. That we're saying in exec mode, just our regular exec prompt as here, that we want to set level 5 and all commands that begin with show. So it's going to do show and show anything. We can be more granular and specific in that by adding an additional command onto the end of show here in this privilege command, but we wanted to allow all show commands for level 5. Now we might not want them to be able to make changes, but we want to allow them to take a look at everything. Let's say that's what we want our help desk to be able to do our initial discovery of a problem, that they received the call and they got complaints from users that certain things are happening, so they can do show commands and take a look at the router, but we don't want them to actually go making changes. We want to leave that for the senior network engineers, that the help desk can give them their analysis of what's going on. The network engineer can hop in, verify, and make the appropriate changes. So if we wanted to, say, allow them to configure the IP address on an interface, then we need to do a few things. So first, we need to allow the level 5, the privilege level 5, to get to the configure command. Because remember, enable mode is level 15. That by default, level 1 and all levels lower than 15 do not have access to enable mode. That they don't have access to configuration because of that. So we need to go ahead and specify that they are allowed to. So we say that they're allowed to access the configure terminal. Now, when you go ahead and do this and you type in the privilege exec level 5 configure terminal command, that it will automatically go ahead and add the configure command as well. That if you only type in this command and you do a show run, you're going to also see this command in there too, because you have to have the configure parent command allowed before you're allowed to run configure terminal. Similarly, we'll go ahead and say that in the configuration mode, so this is in global configuration mode, that we are allowing the level 5, privilege level 5, to access the interface configuration mode. And then from interface configuration mode, we need to say that privilege level 5 is allowed to access the IP address configuration command. And that when we type that in, it will also allow the IP configuration command. Now, I know it sounds a little complicated and it gets a little more intuitive as you do it. We're going to end up running through a lab here to set up a help desk account and set our enable password and set the commands here so that we are only allowed to do a shut no shut on an interface. And then we're going to log in and we're going to verify that. So let's take a quick look at our lab here. So the steps here are 6 steps. We're going to create a level 15 admin account, and then we're going to create a level 5 help desk account. And mind you, level 5 was just arbitrarily chosen. You could be level 2, you could be level 11, it doesn't matter. That I'm just saying level 5 because that's the number that I picked here, and that you can have multiple different levels and assign various commands to various levels, so that say your routing team specifically has access to just OSPF, EIGRP, BGP, all of your routing protocol commands, but no interface commands or no lawful intercept commands or no capture commands and things of that sort, or that your help desk only has show commands and can do a shut, no shut on an interface, and that we want to allow here. So we're going to set our enable password. We're going to allow the help desk to run all show commands except show run. We'll take a look here and see that when we allow level 5 to run all show commands, just show commands, it excludes show run. That I'll show you there that we are not able to do a show run, that is a level 15 command unless you specify otherwise, that we can allow show run. And that might be fun. We can try that on the end here if we still have some time to go ahead and allow help desk to run the show run command as well. And then we will also set our help desk account to be allowed to shut no shut any interface. That we want to allow them to be able to do basic troubleshooting of, shut no shut an interface. And then we're going to log into the help desk command, and we're going to verify the effects that we created here. So let's go ahead and hop into our router here real quick. Now this router is fresh. I have not made any changes here, so no interfaces have been set. The host name has not even been set. We don't have any usernames or passwords, so we're going to need to go ahead and create that here. So first up, let's go ahead and go enable and config T, and we don't have any password here yet because it has not been set. So let's create our level 15 admin account. Okay, go username, admin, privilege, 15, and then we're going to set our secret. And I'm going to be fancy here and just do admin. Mind you, you would not want to do that in production, of course, but we're just at a lab here, so we're going to make it easy to make sure I don't forget this while we're doing the lab. Awesome. So let's create our privilege level 5 help desk account. Help desk, privilege 5, secret. Let's just do help desk. Awesome. And then we're going to set an enable password. So we're going to go enable secret and set one here. We're just going to do enable. Awesome. And then let's go ahead and do a quick show run. Do show run. I want to show you what that secret command does. Is that it obfuscates our passwords here. That you can see that that's a lot harder to go ahead and read and remember. Mind you, it's very easy to crack. That it is just encrypted in such a way that there are password crackers online. There are websites where you can go and just type in this guy here, and it'll show you the correct password, how that matches up, the plain text password. But this really just prevents the over-the-shoulder attack, where somebody can't just come by while you're looking at the show run and take a look at this and be like, okay, well, I'm just going to type this in later, and be able to steal your password in that way. That this is far more complicated, and it would make it much more difficult for an over-the-shoulder attack. And same thing with our usernames here, is that we've got our username admin privilege 15 and our username helpdesk privilege 5, and our secrets here. They are type 5 encrypted. There's also type 7 encryption that you can take a look at some time here. You see that in like Cisco ASAs and such. So now, step 4. Let's go ahead and allow helpdesk to run all show commands except show run. So here we're going to go ahead and do privilege exec level 5. That's going to be all show commands. And then that's all. It's just privilege exec level 5 show. Now let's go ahead and take a quick look at that and just verify that right now. Let's go end. We'll go log out. And then let's go ahead and log in. Log in as our helpdesk user. Great. And now let's go ahead and try and just go into configure terminal. Boom. We cannot. Now let's go ahead and just take a look at show. Well, we've got a whole lot of show commands here. A whole lot. It would even seem all of them. If we do show IP interface brief, great. If we do show IP OSPF, cool. It's not giving us an error. We just don't have OSPF configured. Show SNMP. SNMP agent is not enabled. No worries. We didn't get a error because we're allowed to run that command. Now let's do a show run. Now, invalid input detected. We are not allowed to run the show run command because that is a level 15 command by default. But we could do like show spanning tree. There's no spanning tree instance, so on and so forth. Awesome. So let's go ahead and continue on to the next step here of allowing the helpdesk user to shut no shut any interface. So we want to make sure this helpdesk user actually has some ability to take some troubleshooting action. So we're going to allow them to shut no shut an interface, and then that's all. So let's go ahead and log in as our admin account. And now we can get back into our configure terminal. And now we'll go privilege exec. Remember, we need to allow level 5 to get into the configure terminal. command. So we'll do exec level 5 configure terminal. Awesome. And then now that we're allowing them to get into global configuration mode, we need to allow them to get into interface configuration mode. So we'll go privilege configure level 5 interface. Awesome. And then now that they can get into interface configuration mode, we need to allow them to run some commands here, right? As right now, they could get into interface configuration mode, but can't do anything. And let's just go ahead and prove that real quick. Let's go back and end. Let's log in as our help desk account. Help desk. Great. We'll go config T. Great. Now we're in global configuration mode. If I do a question mark here, man, I do not have a whole lot of configuration options here. That I do see that I have the interface configuration mode here. So I'll go interface. Let's just go into interface fast 00. Awesome. If I do a question mark here, man, that's pretty sparse. I don't have any access here at all. I can't do anything. So now that they can get into interface configuration mode for any interface, they can't actually do anything there. So let's go ahead and allow the shut command and the no shut command as well. And so when you allow one command, you do allow the no version of that command by default as well, that you can negate any command that you allow. So we don't need to explicitly allow no shut. So let's go end, log in, log back in as our admin account. Let's go privilege interface. So for the interface configuration mode, level 5. And then here we're going to allow the shutdown command. Awesome. Let's go end, log in as our help desk account. Let's go into config T. Actually, let's do a show IP interface brief. Whoops. We can see, man, well, they're saying this doesn't work, and it's probably because none of the interfaces are enabled here right now, that they're all administratively down. So thinking that that's what we got to do, let's jump into fast 01 and enable that interface. So if we go config T and go interface fast 01, awesome. And then here we've got the shutdown command. So let's go no shut. Awesome. So that, now if we do a do show IP interface brief, whoops. That's not going to let us from the, we don't have the do command here. Let's go and we'll do show IP interface brief. And we now see that our interface is now up. We don't have an IP address assigned. We don't have the ability to assign an IP address, but that is now up because we had the shutdown command allowed. Now still, if we do a show run, we don't have access to the show run. Real quick, let's go into our admin account. Let's allow the show running config command for our help desk user that we want to have them be able to confirm our config. They can't make many changes to it. They can only do a no shut or shut down on an interface, but at least we want them to be able to see our running config. So we're going to do privilege. Oops. Get into global configuration mode. Privilege exec level 5 show run. Awesome. Let's go end, log in as our help desk account and do a show run. And then now we can take a look at our running config here. But mind you, still, if we go into config T and take a look here, we don't really have a whole lot of access. We can't go to router OSPF 100 because we don't have access to the router command or the subcommands of OSPF. So that's how you do access control and privilege levels in Cisco iOS and assign them to a username, you can see that you can get pretty granular with this, that it takes a little while to go ahead and get your access control set up, but as an organization, you may choose to go about access control in this manner and just have a standard set of privilege commands that you save in a document somewhere, that whenever you're spinning up a new router or a new switch, this is the access control commands, the base configuration that you put into your device, so that you set your different departments and your different user accounts to have the correct access for your organization and how you manage that. Awesome. So just like the others, let's run through a couple of practice questions here before we end off. First up, when a staff member tries to log into a corporate resource with a username and password, they are then sent an email with a confirmation code that must be entered. What type of authentication method is in place? Is it simple password authentication, authorization, multi-factor authentication, or TOTP, time-based one-time password? Now, this would be an example where putting in the password was a single factor, and then getting an email was a second factor for authentication. So this is an example of multi-factor authentication. The answer is C. And finally, a help desk engineer connects to a router in your organization and runs a few show commands, then attempts to make a change but finds they are unable to and need a senior engineer to perform. What does the engineer's identity not have that's needed to perform the task? Permission, authentication, authorization, or accounting? Now remember, the help desk user obviously logged into the device because they are able to get in there, but they are unable to run the commands that are needed, so they are not authorized for running those commands. That the answer here would be authorization. Their identity does not have authorization needed to perform the task. Now, I hope that this has been informative for you, and I would like to thank you for viewing. Virtual private networks. Now, the CCNA exam topics specifically says that we need to describe remote access and site-to-site VPNs. So we won't be going over their configuration in iOS, but we will be going over what they are and generally how they work. There's going to be a little bit of detail we won't go through here, but this one is going to be one of the longer videos. There's going to be a lot of text here, so just stay with me, rewatch this a couple times if you need to, and let's jump through it. So first up, let's just talk about a virtual private network. What is that really? So a private network can generally be, your LAN, your local area network, and usually you'll use your RFC 1918 address space in that LAN, your private IP address space where the private network would be, and that this is your corporate network. And a virtual private network is where you are not physically there. Say you've got your HQ over here and you've got person's house over here, and then you've got the internet in the middle. And then you go ahead and have them connect through the internet over to your HQ. Now this method of connecting to the HQ, maybe they're using a software client to go ahead and actually get routes to route their traffic over there. That's just generic traffic that could be anything. That could be using proprietary software. That could be accessing file shares or internal web resources, RDP into servers, what have you. Or they could be using a clientless solution. You could have it where their entire, maybe this is a small office here actually, instead of a house, and that you now have 5 or 6 employees here, and that you now have a site to site or a LAN to LAN VPN. That's a virtual private network where you are creating a tunnel that is reasonably secure and considered to be private, and that you're connecting these two LANs or these two locations through a virtual network. So first up, site-to-site VPNs. You'll see it abbreviated a lot as S2S VPNs. Let's just do a quick overview here. They're sometimes also called LAN-to-LAN VPN. So you'll see them in devices, perhaps some older ASA software as L2L VPN. That's how you'll see that abbreviated in the configuration sometimes. As the name implies, it connects two networks using a VPN endpoint. So a LAN to LAN is you're using a router. You've got router 1, router 2, you're forming a tunnel between them such that router connects to switch and router connects to switch, and that you've got, these workstations over here that are connecting over to the switch, and that they are using the router here where it's sending your traffic through that tunnel to this router to access, some device over here, maybe a server, maybe another workstation, what have you. That it is a LAN to LAN VPN. So the VPN endpoints here, those are your routers or your firewalls that are creating the tunnel between them. That what they do is they create a security association, an SA between each other. And what is a security association? It's really just an agreement on the parameters for encapsulation and decapsulation of traffic. What does that mean? That means that when we go ahead and encapsulate traffic, we're actually adding on, additional header items onto the traffic, where we are either verifying the confidentiality of the traffic, maybe we're encrypting it to ensure confidentiality, or that we are verifying integrity and authenticity of the traffic, that we are authenticating, stating that yes, this traffic actually originates from router A here, that when router B, and that the response traffic, we can authenticate router B and verify that that traffic actually originated from router B, and that there's not just some black hat hacker here in the middle injecting traffic into the middle for router A to think that it's talking to router B. And so the VPNs can be built using two different logical methods here, and that's route-based and policy-based. So these are a little different. The way that route-based VPN works is that you create a generic security association between the two routers here, between the two endpoints. You create this tunnel that can have any traffic. That on the router over here, on router A, in that security association, the route-based security association, it's agreeing to encapsulate or decapsulate any traffic that is pointed out a virtual tunnel interface. That's how you'll see route-based referenced in Cisco a lot, is as a VTI, a virtual tunnel interface, such that any traffic whose exit interface is the VTI will get encrypted or encapsulated and sent over to router B through that SA that the VTI is associated with. And vice versa, on router B, any traffic whose ingress interface, the inbound interface, is the VTI, will be decapsulated or de-encrypted. It doesn't care what source or destination IP address is in there. It's going to go ahead and decrypt that because the inbound interface was the VTI. Whereas with policy-based, you are creating ACLs, access control lists, which we'll go over in another video, the next one actually, that identify interesting traffic. You'll see that phrase a lot, interesting traffic, where it is traffic which is interesting to this security association, that traffic which matches it, which can be a specific source or destination, IP address or network, that traffic is then encrypted and sent across the line, and when router B receives that traffic must also be in its interesting traffic. Is that you actually have two-way security association here, is that this sends outbound, but then this is receiving as well. That's a reception security association, and there's also a sending security association. So in the traffic that router B receives, it needs to match those ACLs. It needs to be interesting for it to go ahead and decrypt that traffic or decapsulate that traffic. and vice versa, any traffic going back, any traffic going from router B to router A, that needs to match against ACLs in router B. And what that actually is, it's a crypto map. That it has ACLs that match in the crypto map so that it gets encrypted and sent over to router A, and then likewise router A, that traffic needs to be interesting to router A. It needs to be in that crypto map and match against it in order for router A to decrypt it and send it out to its destination. So let's talk a little bit about the protocols used in site-to-site VPNs. So site-to-sites typically use the IPsec suite of protocols. That IPsec in and of itself is not a protocol, but it is a suite of protocols. And that there are three protocols used here. That it's the authentication header, AH, encapsulating security protocol, ESP, and the internet key exchange, which is more of a process than anything else. We'll talk about that in a little more detail here and how that occurs very shortly. AH and ESP, these are not transport protocols. These don't ride on top of, these are transport protocols. They don't ride on top of TCP or UDP, that they are their own protocols. They are IP protocol number 51 and 50. 50 for ESP and 51 for AH. AH does not provide any encryption. It only provides authentication, and it can verify data integrity and authenticity, but it provides no data confidentiality. And that our site-to-site VPN, it's intended to ensure CIA. You'll see that referenced in some places. Confidentiality, integrity, and authenticity. That ESP provides the encryption here and allows for that to happen. So then you actually get your confidentiality of your data there. Now over here to take a quick look at the header information and the encryption scope and authentication scope for AH and ESP. That IKE version 2, so there's actually two versions of IKE. There's IKE V1, that's just not going to work. There's IKE V1 and V2. That IKE version 2, there's no such thing as using AH with ESP. It's just using ESP for phase 1 and phase 2. So ESP encrypts your full IP header and TCP header and your data, and it actually encapsulates it. It has a header and a tail on there. That this is in tunnel mode, right, rather than transport mode. There's two different modes that we can use, but tunnel mode is a site-to-site VPN, whereas transport mode is IPsec for host-to-host VPN. And although you could justify that as being site-to-site with one host on each side, in reality, that's not what Cisco's talking about here. We're talking about site-to-site tunnel mode VPNs. That I would be familiar with this graph here just to understand what's going on. That, the full packet here, when you send a packet, say you've got, this guy here at 10.1.1.1, and he's sending a packet over here to this guy at 172.16.1.1. And that we've got our routers in between with a security association built between them, that when this guy sends a packet over to 172.116.1.1, remember that packet, that's going to have in the IP header here, that's going to have the source IP address of 10.1.1.1 and the destination IP address of 172.16.1.1, and that whole header there is actually encrypted. That those private IP addresses and the TCP header or UDP header or any other protocol that you're using and the data all inside of it, that all gets encrypted. So you cannot see or at least not easily without decrypting the packet. You can't see this information in that packet. That we are adding a new IP header onto the outside here where it's using the source IP address, and this is traveling across the internet, right, or some other maybe internal network, and you want to use a VPN internally because you don't trust those marketing guys and you really think they're trying to snoop in on your traffic when this has to go and traverse through their network or their router. and it's using the source IP address, right, of this interface of this router and the destination IP destination IP address of this interface here. And that when it receives it, it'll go ahead and decrypt it and be able to check. Now, ESP does have an authentication scope where you are authenticating this encrypted traffic here with the ESP header. And that authentication also provides integrity, where you are doing a checksum to make sure, and you're hashing and including that hash to make sure that when it's decrypted and hashed, that the other side can confirm that the data is actually indeed the same, and that it has not been tampered with at some point in the middle between it being transmitted and received. Now, continuing along with the protocols a little bit here, I said we were going to talk about IKE and the phases a little more. So IKE is the Internet Key Exchange, and something that's heavily used by IKE is the Diffie-Hellman algorithm. You'll see that referenced quite a lot in the Diffie-Hellman groups. That Diffie-Hellman were two different people, and that they developed this algorithm which is used for secure key exchange and generation. It does not provide any security or encryption. It's just used for key exchange, for creating a secret key to use during encryption and being able to transmit that and making sure that both sides have this when they're talking over an unsecure channel. Now, when you have a router here and a router here and they're connected over the internet, right, that this connection that's over the public internet and that you're not encrypting any traffic, that is called an unsecure channel. It's a public transport that anybody could be looking in on that you don't know. It could be that all of your traffic is being routed through some router and somebody's home somewhere, and you don't know. Your traffic just gets to the other side, and they could be snooping in on everything. So that is an unsecure channel, and that you need a way of creating a secure channel on the fly without, walking over there and handing them a secret key to use for the encryption. And the way that's done is with Diffie-Hellman. And that you can see the simplification or the idea of how Diffie-Hellman works here is that you start with some common key that you go ahead and exchange, that you can exchange that key without problem, and you create for yourself a secret key or a secret color here, and that you mix these two, and that you make it so that when they're mixed, unmixing these, kind of like using paint, right, is you're mixing the paint and you're creating a new color, and that it's very expensive to try and unmix these and find out what the secret is and the two colors that are contained within this mixed color. And think about it, it's like, mixing yellow and green. You end up getting blue here apparently, and that it's really hard to go ahead and actually get yellow and green out of that. So you go ahead and transport these to the other side, and that they end up adding their own secret color to it again, and that creates now our common secret that ends up with the same color. Or the same secret here on each side, that it was very difficult to figure out what this common secret is because you don't know what this color is, what this secret color is. And that you end up getting the same color on each side here. So that's a way of exchanging secret keys and creating them without having a secure channel. And then you can now create a secure channel using those secret keys. And that's what's done during phase 1. So IPsec tunnels are built using IKE, the Internet Key Exchange, in 2 phases. That in phase 1, the unencrypted channel for Diffie-Hellman exchange, that the keys are exchanged using are used for building the encrypted channel, is that your common secret here now, the brown, that this is now used for creating a secure channel. and that this channel, the Phase 1 Security Association, is called an ISACAMP Security Association. That's the Internet Security Association and Key Management Protocol. That's a specific protocol used to go ahead and create this security association. And that now that you have a secure channel, you can go ahead and exchange secret keys again, and go ahead and create new ones and create a new secret channel or secured channel using that other secured channel. And that makes it so that you can be relatively sure that this cannot be compromised. That even if one side of this were compromised, that since we're using Diffie-Hellman again within our secure channel, you can be reasonably sure that the Phase 2 secure channel is now actually secure, that it is called perfect forward secrecy, or PFS, that Diffie-Hellman can be used in the Phase 1 encrypted channel to create the Phase 2 encrypted channel. And that this Phase 2 is an IPsec SA, your IPsec Security Association. That's what the Phase 2 Security Association is called. Now, to go over the algorithms a little bit here, is the things that you'll see, your encryption algorithms that are used in site-to-site VPNs, that these are your data encryption standard, or DES, or your triple data encryption standard, which is really just DES run 3 times, which is why it's called triple DES. Or the advanced encryption standard, AES. This is what is the standard right now and is what is recommended to be used. The use of DES, just standard DES, is discouraged in one of the RFCs, in RFC 4835. If you absolutely have to make legacy devices work, all right, so be it, but you really should not. You should just upgrade that device and get something that can support a more advanced encryption standard like AES, and go from there. And triple DES is just not recommended, that Cisco doesn't recommend using it. That it suffers from the same potential problems as DES, although because you're running the same thing 3 times, it makes it significantly more difficult, and it's just not recommended that you use that. Now, for your message authentication and integrity check, we use HMAC, hash-based message authentication. And the algorithms that are used are HMAC MD5, HMAC SHA-1, or HMAC SHA-256, and there are many others as well that you can use, but the one to point out here is that MD5, although it's considered safe, it is legacy and is not recommended that you continue using it. That you should use SHA and some high bit level of SHA, like SHA-256. And the way that a hash works, right, is that a hash is where you create a message digest. And a hash is a one-way algorithm. This means that given the hash value here, that I cannot get my message out of this hash value. This is not an encryption where it's two-way, where you can decrypt this. No, it's creating a digest of it, where you can say that each message here will generally create a unique hash value. Now, of course, it does not always. Say that you have, the message and it just says the word Bob in it, and that creates a hash that looks like this. Well, this is where a rainbow attack comes in, is where you can go ahead and find that, the message 1612B72, that this, by chance, because of the way that your hashing algorithm works, ends up creating the same hash value. And that now your message could contain this, or it could contain Bob. And that both will end up giving you the same hash value, so both of them will end up being equivalent and saying, yep, the integrity is just fine, even though obviously the actual contents are not the same. Now, the way that hashing algorithms work, very small changes in your messages will create very large changes in your hash, so that you can be reasonably sure that your message is not changed, and it's all about being reasonably sure here, right? So that's the overview of site-to-site VPNs or LAN-to-LAN VPNs. So let's talk a little bit about remote access VPNs. They're often abbreviated as RAVPN. So they're also sometimes called point-to-site VPN because typically you are using an individual computer to connect into a network, and that you can access many devices in that network from your single point. So it's point-to-site rather than a site-to-site. And that it connects a single host to the corporate network or resources securely, and it can be deployed using one or both of two different models. And it's either client-based or clientless. And we'll talk a little bit about what each of those are, starting first up with a clientless remote access VPN solution. So the way a clientless VPN solution works is that it's done through a web interface. That you're authenticating through a web portal, right? And that from here, we can go ahead and access, internal addresses or internal devices or the intranet and through a web interface. You can also deploy web applications through JavaScript and things like that. I've seen where you can actually do remote desktop through a web interface here and be able to access, or VNC to be able to get into Linux boxes or your Windows boxes, what have you. And that it uses HTTPS to access resources securely. Now, HTTPS, the S on there, right, is actually SSL. And more recently, it's, TLS, actually, is what's used, the Transport Layer Security. And it's the Hypertext Transfer Protocol. That this is the protocol that's being used to actually give you the data that you're looking to obtain from your remote network, from your corporate resources. And that you could browse the network or get to files and things of that sort and do that through your clientless VPN here, that it's all through a web interface. Now that's fine, but it doesn't work for everything. And also, it can be a little cumbersome. That accessing all of your corporate resources through a web interface like this, that is not just like being at the office. That's not opening up your Windows Explorer and going to your S drive and getting to your files that way and saving your documents that you need or printing them to the printer by just clicking the print button. No, you got to change your method of working a little bit here, that this is just not quite the same. And that's where client-based VPNs come into place. That they are typically, quote, just like being at the office. And that's, a quote from Cisco, that's how they describe client-based VPNs. And that they utilize a software client installed on the user's machine to enhance the VPN experience, to actually add a virtual interface onto your computer, typically, along with injecting routes into the route table on your computer, so that, traffic destined for certain IPs ends up getting put through your virtual tunnel interface on your computer and encrypted and sent over to your office, and the return traffic gets decrypted accordingly, of course. And that these can operate using either IPsec or SSL. That SSL is actually a little bit of a newer feature for remote access VPNs. By a little bit, I mean it's a handful of years, but still, SSL remote access VPNs had not been around for the longest time, at least client-based SSL VPNs. That for a long time, SSL VPN really meant clientless VPN. And that, any client-based was all IPsec, but now they've been able to go ahead and create client-based SSL VPNs, which use the SSL tunnel, as in HTTPS, the SSL from that, to tunnel other traffic than just Hypertext Transfer Protocol, to tunnel other protocols like TCP and UDP across using SSL. And that IPsec, in this case, IKE uses UDP port 500 and ESP over NAT traversal, because most of your workstations, your end users, they're going to be at home using their client-based VPN, and that they're going to be behind a NAT device because they don't have a public IP address directly assigned to their workstation at home. So it has to traverse a NAT device, and it uses UDP 4500. So if you ever have a firewall problem where they're not able to connect, you might want to go ahead and double check that 500 and 4500 are allowed outbound through their firewall. And it's because remote users are typically behind NAT.
Awesome. Now, I know that that was a little intense and that there's a lot of information there. If you need to run back through it, of course, go ahead and do so. But just like the others, let's run through a couple of practice questions before we end off. First up, what IP protocol is encapsulating security protocol? Is it over TCP? Is it IP protocol 50? Over UDP? Or IP protocol 51? Now, this was really just meant to drive home the point that ESP and AH are their own IP protocol. They don't operate over TCP or UDP by default. That ESP is IP protocol number 50. And finally, what security associations are created during each phase? Is phase 1 ISACAMP and phase 2 is IPsec? Is phase 1 IPsec and phase 2 is IKE? Is phase 1 ISACAMP and phase 2 is IKE? Or is phase 1 IKE and phase 2 is IPsec? Now, the phase 1 security association is called an ISACAMP security association, the Internet Security Association and Key Management Protocol. And then the phase 2 security association here is an IPsec SA. This also comes from the fact that when you're in a router, right, and that you're checking your security associations to see if they're actually available, if they've actually been built, that you would do show crypto ISACAMP SA and show crypto IPsec SA, and that will show you the information about your phase 1 and your phase 2 titles respectively. Now, I hope that this has been informative for you, and I would like to thank you for viewing. Access control lists. Most people abbreviate access control lists as ACLs, both when saying them verbally and also when writing them down. And referencing them in documentation, you'll see it as ACL, this ACL, that ACL, create your ACL, etc. ACLs are one of Cisco's most versatile feature sets. That ACLs are used generally to just identify traffic. So we're going to run through what ACLs are used for, how to create standard and extended ACLs and what the difference between them are, and then we're going to go through a lab of creating a couple of ACLs and testing to show what the effect is here and make that very visible for us. So first up, let's just do a brief overview of what ACLs are and why they're used. So, like I said, at the heart, ACLs are used to identify interesting traffic. So that can be used in any circumstance where we need to identify traffic. And this can be in access groups, which is blocking and allowing traffic on an interface, inbound or outbound. Crypto map, identifying traffic for our VPNs and what should be encrypted and what should not. Class maps, identifying traffic just for traffic classes, to be able to put them into policy maps, to be able to do policy-based routing, or perhaps token buckets for shaping or policing. Route maps, to go ahead and specify policy-based routing, or be able to identify what traffic should be distributed into a routing protocol. Or packet captures. We use ACLs to identify the traffic that should be captured in a packet capture to do troubleshooting on our network and view what's going on. There are so many uses for ACLs. You will almost not see all of them, but you certainly can, and there might be a few more interesting topics here or there where you end up finding, oh man, we end up using an ACL for this. So, access control lists. There are two different types. There are standard and extended. So the standard range, as you can see here, when you just do at global configuration, just access-list, there are two different standard ranges for numbered ACLs and two different extended ranges for numbered ACLs. The standard range is 1 to 99 for standard, and then also 1300 to 1999 for the numbered ACLs. And that is the expanded range down here, the 1300 to 1999, and the regular range for standard ACLs is 1 to 99. And then similarly for extended, you've got 100 to 199, and then up here you've got your 2000 to 2699. Now that's for doing access-list. That's a numbered ACL.
you don't have to do numbered ACLs, that you could use a named ACL instead. I prefer this personally, just because you can give your ACL a name which helps you identify what it was used for. You do have the ability to put remarks in your ACLs, and I would highly recommend you do that so you can understand what the ACL was used for or what a particular entry is used for. But even if you don't do that, creating a named ACL by using the IP access list command, you can create a named ACL. You can also create a numbered ACL in that same fashion, and I'll show you that during our lab briefly. But with this, you end up specifying whether you want to create an extended or standard ACL, and then from there you have the option to specify a name, or you can specify a number, and it will give you the ranges available for your numbered ACL if you so choose. So standard and extended ACLs use what's called a wildcard mask instead of a subnet mask. A wildcard mask is a bit inversion of a subnet mask. What do I mean by that? If we take a look down here, right, is that we've got our subnet mask. Now this guy is a /26. So we've got 255.255.255.192, and we see here that we've got 24 bits of ones and the rest being zeros. Now if you do a bit inversion, flip every 1 to a 0 and every 0 to a 1, then we end up with these 6 guys down here that are ones instead of zeros. Our wildcard mask is the inversion of our subnet mask. It is 0.0.0.63. This number here, this dotted decimal notation, is your wildcard mask. This is what you'll end up entering. It's a good thing to remember. If you end up putting in a subnet mask instead, it's going to end up either telling you it's an invalid subnet mask, or if you end up getting unlucky here, you might get really improper results for the masks that you put in, that it's not going to behave the way that you think it will. So both both ACLs, extended and standard, use statement numbers to order the permit deny statements within an ACL. So that's what an ACL has, right? Is it's a bunch of permit this, deny this. Permit source address to destination address, but deny this source address to this destination address over this protocol, which we'll talk about that in a few moments here, that extended ACLs have the ability to identify protocol, whereas standard does not. That it uses statement numbers to order the access control entries, the ACE. You'll see that abbreviated a lot in some graphical interfaces. You'll see where you have the option to add an ACE to an ACL, and that's an access control entry. And that down here, this is what happens when you create a 2-entry ACL. Is that first I popped into a numbered access list. I did access-list number 10, so I'm doing a standard access list, not an extended, and I have a permit statement. I'm permitting 10.1.1.1, and I'm doing all zeros. What does this mean? That translates to a subnet mask of all ones. So this is a host address. It is not a network at all, or a range of addresses. Same thing with the second statement here. So once I pressed enter on that, I was brought back to global configuration mode. And then I just popped in another entry here. I did on to access list number 10. I have a permit statement. I'm doing 10.1.1.2. So I'm permitting 10.1.1.1 and 10.1.1.2. Now you'll see in the next slide, we'll go over standard access lists a little more detail. Standard ACLs only allow you to define a source address or range, or a source subnet. And that it does not care about any destination. That is all it is matching on, is only the source address. No protocol, no destination. So then, after I added those 2 entries to access list number 10, because that's how I am numbering that here, is access list number 10, then if I do a show access-list 10, then it is going to spit it out here for me, and I see that I've got 10 and 20 here. Now, what is that? Those are the statement numbers. This is the entry numbers. Automatically, it will start at 10, and it will bump it up by 10 each time. We go from lowest to highest is how it is going to process this. So we would start at statement number 1 and go ahead and process that and work our way up to statement number 20 if there is a 1, and it'll just start from the lowest statement number and go up to the highest. And then that's how it orders the operation for your access list, and it adds this automatically so that if we come back and say, oh man, we want to go ahead and add a statement in the middle here at 15, then we have the ability to do so. It's not just going to order these by 1 at a time, it's separating them by 10, so you have some flexibility to come back and edit this without having to remove your entire access list and add it back all in again, causing perhaps some downtime for your network or some effects that you don't want to see in your network. Something really, really important and trips everybody up when they are dealing with ACLs the first time is that all ACLs, both standard and extended, have an implicit deny at the end. This is not shown. So here, the standard access list 10, it will permit 10.1.1.1, 10.1.1.2, and up here, there's an implicit deny that denies everything. So it will permit 10.1.1.1 and 10.1.1.2 as source addresses and deny everything else. That you need to remember that it's there. I usually like to put a deny any or a deny any statement at the end just so that I have a visual cue there that there is, rather than an implicit deny, an explicit deny, that you can actually visually see that there's a deny statement there. And then, as we said, ACLs are evaluated from the lowest entry to highest. And the first matching access control entry is used and evaluation stops. So let's say I have a packet coming in, right, and that this ACL number 10 is applied to the interface where that packet is coming in. And let's say that packet has a source IP address of 10.1.1.1. When that packet comes in and this access list 10 is evaluated, it will start from the lowest entry number here, entry number 10, and work its way up. It'll see that our packet matches entry number 10. Entry number 20 will not be evaluated at all. It will never go there. It hits the first matching entry and stops. And then whatever action is listed there, a permit or deny, that is the action that is done to that packet. That's something important to remember, that generally you want your most specific entries at the top and your least specific entries towards the bottom. And I know that this is ordered backwards here. So your most specific entries with the lowest statement numbers and your most specific entries with your lowest statement numbers and your least specific with the highest statement numbers. So our standard ACLs, as we said, they only match on the source IP address, and it's over any IP protocol. That is something to mention, that it is over IP protocol. If you have some other protocol that is not IP, then our access list may not match that, and we might need to use an extended or another method of filtering that traffic. But it only matches the source IP address. So because of that, skipping to this bottom note here, is that it should be configured as close to the destination as possible for best practice. Why? Because if you are configuring this, let's say we've got our workstation here, right? And that our workstation connects up to our router. Let's make that a little cleaner. Connects up to our router connects over to another router. Let's say we've got a server here, and let's say this connects over to another router, and then this connects off into the internet, and then this guy connects over to a router, and that connects to a server. Now let's say we want to block this workstation from accessing this server, and we want to use a standard ACL for it. Why you would do that, I'm not really sure, but Cisco might throw something like that at you. Where are you going to put this standard ACL in order to block this workstation from accessing this server? Well, you're going to put it down here, as close to the destination as possible. If we put that ACL here, then we are blocking this workstation from accessing everything. And if we end up putting it here, we're blocking this workstation from accessing this whole side, so on and so forth. You see where I'm getting here. If we were to put it here, it's going to block access to the internet. If we put it here, then it will only block access to that server there. It's just because of the limitation of standard ACLs that you want to put it as close to the destination as possible so that you're using the physical placement of your ACL as essentially your destination filter there. So, like I said, they can be numbered or named, and the numbering has two different ranges. There are a total of 799 numbering ACL available. And it is 1 through 99 and 1300 through 1999. I would know the ranges for the standard and extended ACLs. Cisco really loves to ask that question as just a little multiple choice. What are the extended range for standard ACLs? And that would be 1300 to 1999. Maybe it'll give you a few options of numbering ranges to choose from. And that when you have a standard ACL that is numbered or named here, we have a numbered ACL here using number 10, and then we have a named ACL here with the name standard-ACL. And that I put actually the statement number 5 on this guy here and said that I want statement number 5 to be permit 10111 and then statement number 10 to be permit 10112. Is that by default it'll start at 10 and increment by 10 each additional entry, but you have the ability to specify what statement number you want your entry to be in. Great. So that's standard ACLs. Let's jump into extended ACLs here. As we said, this matches against both source and destination IP and will do over a specified protocol. Right? So we have many protocols that we can choose from, and we have a lot more flexibility here because this can match over source and destination IPs. And because of that, let's skip down here, is that it should be configured as close to the source as possible for best practice. And why is that? Because we don't really want to use our bandwidth. If we go back to this slide for just a moment here and this little topology, if we've got an extended ACL, you could put your extended ACL over here and that it would give you the same effect of blocking access to this server, but you've now wasted all of this bandwidth sending your traffic across the whole line here, across the whole circuit, in order for it to just get blocked at this guy, when you could have achieved the same effect of putting that ACL right here at this router and be able to block access specifically to this server's IP address from this workstation's IP address over whichever protocol that you so wish, over TCP or over UDP and a specific port. That you can go ahead and apply that as close to the destination as possible and get the same effect. And that just like standard ACLs, remember, there is a implicit deny, right? And these can also be created as numbered or named ACLs. Here we have numbered extended access list number 100, and that it is permitting everything. It's just a permit IP any. And that with the extended named ACL, we have ext-ACL as our named ACL. We've got a few more entries here where first we're permitting 10111 to any address over IP. And then statement number 2 or statement 20 here, we're permitting 10112 to any. And that we're specifically using the host keyword here, where you could do 10111 with a wildcard mask of 000. But we can use the host keyword to not have to put the wildcard mask there and is specifying that only this one IP address. It just comes out a little nicer and is a little more readable. And then statement 30, we are denying 10111 to any. Now, interestingly, this, statement number 10 would get hit first for any traffic sourcing from 10111 to any destination over IP that we are permitting traffic. So statement 30 would never be hit here because it's first going from the top and going to the bottom. And then at the bottom here, statement 40, we are permitting IP any. So really, this ACL, this extended ACL here that's named, this has no effect. It's just permitting IP any, that 100 and the named here both have the same effect, even though the named has this many more entries in it, that we're just permitting everything. It's permitting 10111, permitting 10112, and this entry 30 doesn't matter because entry 10 overlaps, and then 40 is permitting everything else, so it has the same effect as ACL 100 here. Awesome. So now that we see how to or how extended and standard ACLs work, let's go through a lab and see how they're configured and apply them to interfaces so that we can go ahead and confirm and visually see what the effects are here. So here's going to be our lab. Is that we've got 2 routers down here, and we've got 2 loopback interfaces on each one. I have already configured the host names and the IP addresses on the interfaces and the loopbacks here, and that's all. That we need to go ahead and configure everything else. So our steps in this lab here is that we're going to go ahead and set static routes on each router for the loopback subnets, right? Is that R2 needs to know that we get to these loopbacks by using 10.1.2.1 as the next hop, and same thing, R1 needs to know that we get to 10.2 to these loopbacks here by using 10.1.2.2 as its next hop, right? And then we're going to go ahead and configure each one for SSH briefly. And remember how we do that, right? Is that we need to set a domain name. We need to generate our keys, our RSA keys for use for SSH, and then that will enable SSH. As once we do that, it enables SSH and allows us to go ahead and do that. We will need to go ahead and create a username and password if we actually wanted to log in. I won't really care about, we just care about actually getting that connection there. And then we're going to go ahead and create numbered standard ACL, blocking traffic from 10.1.0.0/24 only, and apply ingress on R2. What does that mean? That means inbound on fast 00 of R2. So for traffic coming in, we're going to go ahead and apply this ACL, blocking traffic sourcing from 10.1.0.0/24. And then we're going to go ahead and ping and verify so that we will ping with a source of 10.1.0.1 and try to ping 10.1.2.2. Try to ping R2 from loopback 0 and see if we're able to. Now, I'll go ahead and do that first once we get our static routes in place to show that we are able to successfully ping, and then we'll get our ACL in place and make sure that we are not able to ping anymore. And then let's go ahead and do that first here, and then we'll address the second half of the lab. So first up, let's head on over to R1. Let's get our static routes in place, and then set it up for SSH, and we'll head on over to R2. So we're going to go ahead and enable config T. We're going to go ahead and do IP route. And our destination is, let's go ahead and just do 10.2.0.0/16. With a next hop of 10.1.2.2. And there we go. And now let's go ahead and set it up for SSH. So we're going to do IP domain name. And we're just going to call this benjtrain.lab. Awesome. And let's go ahead and generate our crypto keys. Awesome. So that's been generated, and it is now enabled SSH. So let's jump on over to R2. And then actually, I didn't show here. I want to do a show IP interface brief. And we've got fast 00 is 10.1.2.1, and then we've got our 2 loopbacks. And then same thing over here. Let's do a show IP interface brief. And we've got 10.1.2.2 and our loopbacks there as well. So let's go ahead and do the same thing as we'll set our IP route 10.1.0.0/16 with a next hop of 10.1.2.1. And then let's go ahead and set our domain name. And let's generate our crypto keys. Excellent. So SSH has been enabled. Great. So then now let's go ahead and over on R1, let's do a ping. And let's go ahead and ping 10.1.2.2 with a source of our loopback 0, right? Of our 10.1.0.1. So we can go ahead and do a source interface, or we can do a source address. Let's go ahead and do a source of loopback 0. Now, it had to go ahead and ARP out first, and then every other one was successful. Let's just check one more time. There we go. Our pings are successful, that we do have routes on both sides, so that R2 knows how to get back to the 10.1.0 network, and that we're able to go ahead and ping that here. And just to make sure, let's go ahead and ping the loopback 0 of R2 here. That is 10.2.0.1 is the IP address of that, and that is also successful here. Awesome. So then now, let's just jump back here. We need to go ahead and create a numbered standard ACL blocking traffic from 10.1.0.0/24 only, and apply ingress on R2. So for that, we need to go over to R2. Let's go to config T. We're going to go ahead and do access-list, and we're going to create a standard. So let's do number 10, and then we're going to deny 10.1.0.0, and it's going to be /24. Remember, this is a wildcard mask, so it is inverse of our subnet mask, and then that's all we got to do. And then now we can go ahead and apply that ingress on an interface, and we do that with the access group command. So if we go to interface fast00, oops, and then do access, whoops, sorry about that. I ran into a little bit of technical difficulty there. So we're at our interface fast00 and need to apply this access list there. So we do with the IP access group command. And then here we created access list 10. And then we're going to apply it inbound on that interface, right? Awesome. So now we need to go ahead and ping and verify that only 10.1.0.0/24 is now blocked, right? Is that we can go back over to router 1 real quick. And let's go ahead and do that. That we're going to ping 10.1.2.2 with a source of loopback 0. And then that is not successful. Awesome. So then let's go ahead and try with the source of loopback 1. That is also not successful. Well, that's not good. Let's go ahead and take off our source and just ping 10.1.2.2. And that's not looking good. Okay. Well, let's find out why here real quick. If we go back over here, let's do a do show IP access list 10. We've got deny 10.1.0.0, and it's the /24, and that's the only entry we have. What could be the issue that we're running into? And it's, well, we forgot about our implicit deny at the end here. So let's go ahead and add in an explicit allow. Let's allow any, so that only the /24 will be matched on the deny, and anything else is allowed. So let's go back to global configuration mode. We're going to go access-list 10, permit any. Awesome. And then now we don't need to reapply it. That should be good to go. If we go back over to R1 and we just try and ping now, that is now successful. If we try and ping with a source of loopback 1, that is successful. If we try and ping with a source of loopback 0, that is not successful. That it is blocking 10.1.0.0/24 network from being able to ping. It's actually blocking that from being able to do anything. So if we tried to ping the loopback 0 of our R2, so 10.2.0.1, that is not successful. However, if we try and ping that with a source of loopback 1, that is successful. That on that interface, all traffic sourcing from 10.1.0.0/24 is denied. That access list is evaluated on all traffic inbound on that interface, whether it's supposed to be routed out somewhere else or to its loopbacks, or if it's to that interface's IP address directly. The ACL on that interface is evaluated first. Awesome. So now let's go take a look at what the second half of our lab is here. Is that we're going to create a named extended ACL blocking only ICMP traffic from 10.1.0.0/16 to 10.2.0.0/16 and apply egress on R1 and ping and verify. So we're only blocking ICMP traffic. That's all, right? So let's go ahead, and this is on R1. We're going to create an extended ACL, and we're going to block ICMP from 10.1.0.0/16 to 10.2.0.0/16. So over on R1, we're going to go config T. We're going to do IP access list just to have a different method of saying this up here. And actually, it's a named extended ACL, so we do need the IP access list command. We're going to make an extended. And then here we can go ahead and create our named ACL. We're going to call it just EXTACL and go enter. And now we're in named extended ACL configuration mode here. And we're going to go ahead and do our first entry. And this is going to be a deny statement. And here we have the different protocols to choose from. Is that it doesn't necessarily have to be just IP. You can choose a different protocol here, or just a specific IP protocol number that you don't necessarily need. If it doesn't match one of these guys, you could just pick the IP protocol number of the traffic. That, as you might know, ESP is IP protocol 50. GRE is its own IP protocol here as well, and ICMP is not, TCP or UDP. It's a different IP protocol. So we're going to deny ICMP from 10.1.0.0/16. So that's 0.0.255.255. Remember, it's the inverse of our subnet mask, and the destination will be 10.2.0.0 with the same wildcard mask. And then we can go ahead and specify the ICMP message type. But we're not going to do that. We're just going to say any ICMP traffic is denied. And then we need to go ahead and allow everything else. So now we're going to do a permit IP any. Awesome. And then we're going to apply that egress on the fast00 interface. So let's go ahead and exit out of our extended named ACL configuration mode and go interface fast00, go IP access group. And then here we're going to apply the EXTACL outbound. Awesome. So now this should deny us from being able to ping anything on R2. That if R1 tries to ping R2, it should not be able to do so. So let's go ahead and try that. Let's try just ping 10.1.2.2. And that is successful. Let's try it with a source of 10.1.0.1. That is not successful. What about 10.1.1.1? That is successful. Now, why might this be? Now, this is actually an interesting thing that applies to this kind of circumstance, is that the interface ACL does not apply to traffic sourcing from the router itself. Now, this is actually showing that I created this lab a little hastily here, and notice that we ran into actually what is a good point, is that the outbound access lists do not apply to traffic sourced from the router itself. So we can get the same effect here by doing an inbound extended ACL on the R2 and go ahead and show that here. Or just do inbound on R1 and reverse our ACL, perhaps add in another entry sourcing from 10.2/16 to destination of 10.1/16, and then we can go ahead and do it inbound and show that this does work. That it's a good point that traffic sourced from the router itself does not filter through interface level ACLs here. And that's something to remember, that you could get tripped up by that in the future as well. So let's go ahead and switch the direction here and add in another entry. So if we go config T, and first let's do a do show IP access list. So what we want to do is we can just add in another entry, or we can remove this entry here and then add in a new one that is reversing the source and destination. So let's go to IP access list configuration mode extended. It's the EXT ACL access list. And then we're going to do a no. And then we're going to add it back in of 10 deny ICMP 10.200/16 to destination of 10.100/16. Awesome. And then let's go ahead and exit. Let's go over to our interface fast00. Let's do a no IP access group EXTACL. Oops. Out. And let's do an IP access group EXTACL inbound instead. Awesome. So now we can go over to router 2, and we should no longer be able to ping router 1 with a source IP address of either of our loopbacks. So if we go ping 10.1.2.1, oops, 10.1.2.1 with a source of our loopback 0, oh, we gotta go to enable mode. There we go. Ping 10.1.2.1 with a source of loopback 0. That is not successful. And with a source of loopback 1, that is also not successful. That we see with a source address of 10.2.0.1 and a source address of 10.2.1.1 that is not successful. Whoops. And now if we go ahead and just do ping 10.1.2.1, that has a source address of 10.1.2.2, so that is successful because that is not matching our access group there. And then we can go ahead and show that we can try to SSH with a source of loopback 0 or 1, and that is not successful, although we are unable to ping. So if we go config T and do SSH, oops, source interface, and do loopback 0. And now let's go ahead and go SSH 10.1.2.1. Whoops. We'll go -L, whatever, Cisco. It's just going to tell us that it doesn't exist anyway, or that the username isn't there, but this should none 2.1. Actually, we are able to connect here, and it's asking for our password that we are unable to ping, but we are able to SSH, and we are SSHing with a source interface of loopback 0. Awesome. Now, just like the other sections, let's run through a couple of practice questions here before we end off. So first up, you have applied the below ACL ingress on fast00 of R2 and then suddenly lost connection to R2 via SSH from the server. Why did you lose connection? So this is the topology that we are considering here. That you are on the server and that you are SSH'd into R2 and that you have created this extended named ACL and that you have applied it inbound on fast 00, and that you have lost access, that you are trying to block 172.17.1.0/24, which actually you blocked 172.17.00/16 inbound on fast 00. So why is this? Is it that the wildcard mask does not match the subnet to be blocked? That we've got a /24 here, but you're doing a /16 here? Is it that this is expected because the access control entry is denying access from the server subnet? Well, no, the ACE is not denying access from the server subnet because we have .16 here and we are doing .17 here, and that this is a /16, so this octet is not considered when using the wildcard mask? Or is it that the server's access is being denied by the implicit deny at the end of the ACL? That certainly seems very possible. If we're taking a look at the entire ACL here, which we should assume we are, then that definitely seems possible. Or is it that the ACL should have been applied egress instead of ingress on fast 00? That doesn't really make sense. So the answer is actually C here, is that we have, remember, that deny any here at the end. It's an implicit deny. That's why I like to put that deny there sometimes so that we can visually see that it is indeed there. So the answer here is C, that you have the implicit deny at the end. So this access list is actually denying all traffic because it is not permitting anything, and that you needed to add a permit any on the end if you wanted to permit any other traffic. Awesome. So then lastly here, considering the below ACL, which answer best describes the effect when applied? That, take a look at this ACL. We've got 4 entries: a permit IP host 10.1.1.1 to destination any, permit IP host 10.1.1.2 to destination any, deny host 10.1.1.1 to destination any, and then permit IP any. Is the effect that all traffic from any source is permitted to any destination, or that traffic sourced from 10.1.1.1 is denied and all other traffic is permitted? Traffic sourced from 10.1.1.1 and 10.1.1.2 is permitted, but nothing else because of our implicit deny at the end? Or is it that all traffic from any source to any destination is denied? Well, I'm sure that instantly doesn't make sense, so D is not the answer. The answer here is A, that entry number 30 here will never be read because entry number 10 overlaps with it and is a permit. So that is permitted, this is permitted, and then everything is permitted. So we are having no deny statements take any effect, so all traffic from any source or destination is allowed. I hope that this has been informative for you, and I'd like to thank you for viewing.
Layer 2 security. At Layer 2, we don't have a lot of the security options that we do at Layer 3, right? We don't have our firewalls, our zone-based firewalls, and doing ACLs and be able to do Layer 4 inspection and things like that. We're in a broadcast domain, and we're looking for maximum speed, right? Is that you have your switches that are ASIC-based. They forward traffic at nearly wire speed, that as soon as a frame comes in, it's going out the other interface where it's supposed to. So we do need some security measures at Layer 2 to prevent any unexpected or unwanted devices from coming onto our network and potentially causing some problems. So in this video here, we're going to go over dynamic ARP inspection, DHCP snooping, and port security. We're going to talk about each one of them and what they do, their purpose, and how they're configured, and then we're going to go through a lab and configure each of them and show what it looks like when it's actually working, and also what happens when you have a violation, when they are doing their job and preventing some unwanted device coming onto the network. So just as a brief overview here, at Layer 2 security technologies, you're going to implement them at your access layer. This is where these technologies will live. And that fundamentally they prevent unwanted devices from accessing the network at Layer 2. And
we're going to be going over the port security, DHCP snooping, and dynamic ARP inspection. So first up, let's talk about port security. So port security limits the number of MAC addresses allowed on a port. Think about this, right, is that if I've got a switch here, and I've got a server here, and that it's connected into the switch, the server, let's say this is a physical machine, right, and that we only have one machine there, we don't have any virtual machines, and when it transmits traffic onto the line here, then the switch does what its primary job is, right, is it learns what MAC address lives off of what ports, so that it can properly forward the responses, or any other traffic that's destined for that MAC address. Now, if you have port security enabled, by default, it only allows one MAC address per an interface. So when I send this traffic into the switch, it will learn that this MAC address, this let's call it 1.1. or 1.1.1.1.1.1, that's the MAC address. I know that that's not a real MAC address, but it will learn that that MAC address is on that port, and any additional MAC addresses that come in on that port, it will go ahead and shut that port down. It'll say that something is wrong here, someone is putting additional traffic onto the line, and that this is not okay. Now, think about it though as well, if you have this enabled and you have a hypervisor here instead of just a single physical machine, that you might have many virtual machines right inside of this single physical machine, and typically the way the virtual networking works with these hypervisors is that you will have a MAC address for each of the network adapters of the virtual machines. So all of that traffic that's being forwarded over into the switch, that's all going to have a bunch of different MAC addresses as the sources there. So all of these machines kind of look like physical machines, right, that live off of this interface of the switch. And it'll say that all of these physical machines, all of these MAC addresses, all live off of that interface. So when you're configuring this, you'll need to take that into consideration, that you might actually have more than one MAC address living off of an interface, even though you only have a single physical device or machine. So the default violation for port security is that it shuts down the offending port. And actually, it doesn't just shut it down, it places it into error disable state. Now, this is a special kind of state for a interface. When you see that an interface is in error disable, the only way to take it out of error disable is, well, there's one of two ways. The primary method is that you need to do a shut, no shut on the interface. You, the administrator, actually need to go and do a shutdown and then a no shutdown, and then that will bring it out of error disable state. However, if you haven't resolved the situation that caused it to go into error disable to begin with, then it will likely return to that state almost immediately anyway. With the shutdown violation action here, that you see there are three different actions that we can choose from. The shutdown action causes it to go to error disable state, and it also logs a system log message, and an SNMP trap is sent if you have SNMP configured. There are also protect and restrict. Let's say you don't want to error disable the interface and cause problems where you, the administrator, need to physically go and correct this. That say you want it to just drop the frame. Well, that's what protect and restrict will do. Protect will just drop the offending frames, so it'll learn what MAC address is on there for the first frame that comes in, and if additional frames come in with different source MAC addresses, those frames are just dropped. Whereas the frames from the original, the learned source MAC address, that is allowed through because that is matching up in the port security database, which will show that it does list the MAC addresses that it has that are secured, and it calls them secure MAC addresses because they are allowed on the interface, and any other non-secure MAC addresses are not allowed on the interface unless more are allowed to be learned dynamically or you manually enter it in as a static entry. Now with protect, right, is that it drops the frame, but it doesn't log anything. It just drops it, but it's not going to tell you anything's happening. This may not be the best situation for you, in which case we'll go with restrict. Restrict will drop the frame, but then it also logs it in the system log, and it sends out an SNMP trap. Very similar to shutdown, but instead of placing it in error disable state, it drops the frame instead. Now we configure this with the switch port security interface command. I show a little screenshot down here. We can end up saying the maximum secure addresses. This is where you would adjust the maximum number of learned MAC addresses on that interface. You can also specify a static entry with the MAC address command. And then we could also specify what the violation action is. This is where you would specify that is in your interface level configuration. When you're setting or enabling port security, you would specify your violation action if you don't want it to be the shutdown action. And then you could also set aging, such that after a certain period of time of inactivity or a certain period of absolute time, so from the time that it was learned, rather than just of inactivity, of not receiving a frame from that address, after a certain period of time, it will clear that address as a secure address. That it will say that another MAC address is now allowed to take its place and be learned dynamically because it is clearing that dynamically learned MAC address from the database for that port there. So continuing a little further here is that, like I said, port security defaults to limiting one MAC address per port it's enabled on, and that you would use the switch port security maximum command in order to adjust that. MAC addresses learned on a port are cleared after the port goes down or the switch is rebooted. So there is such a thing called switch port security MAC address sticky, and you call it sticky MACs for short, typically. If you go ahead and Google this, that's usually how you would see that referenced, and that will cause the dynamically learned MAC addresses for port security to be entered in the running configuration. And specifically, it's in the running config, right? Is that if it reboots, well, your running config is gone unless you saved that to your startup config. So if you do have sticky MACs enabled, you'll want to go ahead and get all of the MAC addresses, turn on all the machines where it's supposed to learn the MAC addresses for port security, and then save your running config so that is now persistent through switch reboots. Now, if you go ahead and unplug an interface and plug it back in, or unplug a cable, then the port will go down, and that the learned MAC addresses on that interface are cleared, which would mean that if you learned a MAC address on the interface, you unplug that cable, plug something else in that now has a new MAC address, then that will actually be allowed because it cleared that MAC address from the table because that port went down. Now, of course, this does not apply if you use sticky MACs. Because that is going into the running configuration, it's now essentially a static MAC entry for the port security database. So bringing the interface down and bring it back up won't do anything for that. That's only for just dynamic without sticky. And by default, aging is disabled, that they do not age out after any period of time. They will stay there indefinitely. And the port must be defined as an access or trunk enabled port, or port security will not allow you to enable it. You'll end up getting this error down here, command rejected, that it is a dynamic port, that you must either specify it as an access port or a trunk port in order to enable port security. And then finally, to go ahead and verify your port security configuration, is use the show port security or show port security interface commands. So when you do show port security, is you've got your interface here with port security enabled, and that it says what is the maximum number of addresses that are allowed to be secured, and we have it configured as the default 1. How many addresses are currently secured? And right now there is 1. It has received 1 MAC address. And it has secured it because it is allowed 1 MAC address. And how many violations has this interface encountered? And it has been 0. There have been no violations, so no additional MAC addresses have tried to appear on that interface since this 1 address was secured. And then looking at the show port security interface command here and specifying the interface, as this gives you a little more detail. That this will show you the last source MAC address and VLAN. That here's the MAC address that appeared on the interface, and it was on VLAN 1. And it'll show you that port security is enabled and that it is secure and up. And the violation mode is set to shutdown, which we saw that here, the security action. the aging time, 0 minutes means that it is not enabled, and that it is defaulting to absolute, but 0 minutes means that it is not aging out. So that's fine. And secure static address aging is disabled for aging out static addresses. And the maximum MAC addresses, the total, the configured would be statically entered MAC addresses, sticky MAC addresses, ones that have been learned by sticky, and the security violation count as well. Awesome. I know that was a lot of information here. So let's go ahead and go through DHCP snooping. We are going to cover port security in just a little bit when we go into the lab. So, DHCP snooping. It's going to be one of the more fun technology names you're going to say. I really like that it has snoop in there. And at its heart, DHCP snooping is meant to prevent rogue DHCP servers from leasing addresses, right? Is that the worst thing can happen on your network is having a rogue DHCP server. At best, it is just somebody brought in a router from home because they wanted to have more interfaces at their desk. Maybe they brought in their laptop or their Xbox and they wanted to plug it in. So it's like you've got John here, right, who has his workstation and he's got his, one little network drop here, and that plugs over into his workstation. And John's here, he's happy, he's sitting at his desk and he's typing away and playing on his workstation, but he's like, man, I really want to bring in my laptop. So he brings in his laptop, but you don't have wireless set up at your company here yet. So what does he do? He brings in his, little home Linksys router here, right? And goes ahead and takes that connection, plugs it into his little home Linksys router, plugs it into his computer and into his laptop, and he's happy. He's just going along doing these things. But little did he know is that this home Linksys router is actually a DHCP server, and that now your home Linksys router is accidentally handing out addresses to his entire floor, and that a lot of people around him are now all having addresses that start with the 192.168.1 that his home network is, and that they are using his little Linksys router here as their gateway. So all of your computers on that floor are all throttling all their traffic through this one little home device sitting on John's desk, and that it's going to slow everything down. It can cause problems. Your internal internal DNS might not resolve because it's handing out, itself probably as the DNS server, and it can just cause all kinds of havoc, and we really don't want that. And that's the best case scenario. Worst case scenario is this is some malicious person, bad actor that has put a DHCP server out there that might even be handing out addresses in your same subnet, putting out the same DNS servers and just giving itself as a default gateway, and that this can really cause problems. He's taking all of your traffic and having it pass through his device, potentially looking in on all of your traffic and stealing sensitive or confidential information. So what DHCP snooping does is it inspects DHCP messages, and specifically it allows or denies as well DHCP server responses. And while it inspects these DHCP messages, it allows the creation of a DHCP snooping database. And what this is it stores IP address and MAC bindings for all computers that have received a DHCP lease from a DHCP server that is on a trusted port. Is that you need to specify which interface on your switch has a DHCP server on it, and that you need to specify that interface as being a trusted interface, that I trust DHCP server messages coming from this interface or on this interface. And that the database is created and is referenced in other features, as now we have trusted information for IP address to MAC address bindings, and also what VLAN and what interface they live off of. And when DHCP snooping is enabled on a VLAN, the server-side DHCP messages, they're only allowed ingress from the trusted ports. So that's what makes it trusted information. And by default, when you configure DHCP snooping, all interfaces are untrusted. You need to go in and specifically configure one as being trusted. But with that, though, consider this situation, is that you've got your switch, you've got another switch, and you've got workstation, right? let's say these are connected, this guy over here, and we've got DHCP server. Awesome. And then let's say over here we've got rogue DHCP. We're just going to call it rogue. Sitting over here, right? Is that the DHCP server messages, our workstation here, it sends out these broadcasts, right, for DHCP discovers of saying, hello, any DHCP servers, please respond to me. So it will end up getting to both our rogue DHCP server and also our trusted DHCP server. Now, the rogue DHCP server is going to respond with an offer. But since this interface right here is not a trusted interface and we have DHCP snooping enabled here on this switch, then that frame will be dropped. It won't do anything like disable the port, it'll just drop that frame. That frame is not allowed because it's a server-side DHCP frame and it is not on a trusted port. Now when the DHCP server that's trusted receives this and it sends back its frame and you have this port configured as a trusted DHCP snooping port and you have DHCP snooping enabled on this switch here, awesome. That frame is now allowed in and it'll be forwarded. And it's going to get forwarded back out and go back over this way. Now the thing is that also on this switch here, this interface also needs to be a trusted interface because the DHCP server frame, the response, the offer is still being forwarded out or coming ingress on this interface here. And that if you don't leave that as a trusted interface, then that frame will end up being dropped and your DHCP just won't work. So DHCP snooping is configured with IP DHCP snooping VLAN command where you enable it per VLAN. Now it must also be enabled globally. I've run into this problem a few times. I've wondered why DHCP snooping is not working, and I enabled it on the VLAN, but I did not enable it globally. So we actually have two commands here, IP DHCP snooping VLAN and give the VLAN number, and then also just IP DHCP snooping. And that interface trust is configured at the interface configuration level, and it's with the IP DHCP snooping trust command. So the database that is created can be viewed with the show IP DHCP snooping database command, and that we have over here with the do show IP DHCP snooping, that we can see that as well as the database over here. And actually, forgive me, that's not database, this is binding. And we'll go through that during the lab here very shortly. So finally, something that relies heavily on DHCP snooping is dynamic ARP inspection. That DAI, as you'll see it abbreviated most often, it references the DHCP snooping database to verify ARP requests and responses, and to make sure that they're valid. So since you now know what IP address and MAC address live off of each port, then when you send an ARP, right, it's the address resolution protocol, it translates MAC addresses and IP addresses or matches up the two. That when you send an ARP request out sourcing from your MAC address and IP address saying who owns this IP address, tell this IP address, it's sourcing from you as a MAC address, then it has the ability to check and make sure that that's actually correct. Now this protects against ARP poisoning, is that you have the ability, right? Let's say I've got here a switch and we've got a router, that this goes out to the internet, and that we've got a workstation here, and that we've got some bad actor here. And I'm drawing as a hat for black hat, whatever. That's not working. But we've got, some bad actor here. We're just going to go like this. And so when we try to get out to the internet, we're on our workstation here and we're trying to get out to the internet, right? Is that we're going to ARP out for our routers, our gateways, MAC address or IP address so that we know how to forward our traffic, that we're going to have a gateway, right, of like .1. Let's say it's like 10.1.1.1, and that's our gateway. And we're going to ARP out for it saying, who owns this? What MAC address owns this IP address? Now, a bad actor here could go ahead and respond on that behalf and say, ooh, me, I actually own this. Or what's one worse is the bad actor can send out what are called gratuitous ARPs, is it can say, hey, everybody, I own 10.1.1.1. And it'll keep on sending that out. And that's an ARP poisoning attack, to where now all of your traffic is being forwarded over to this guy. In a best case scenario, that's just somebody accidentally configured a duplicate IP address on the network. In a worst case, this person is then forwarding the traffic over to the router, and he's just, getting all of that traffic forwarded through him, and that you are none the wiser, but he's able to take a look at and potentially steal sensitive or confidential information. And that is something we definitely don't want to happen. So we want to verify that ARP requests and responses are actually valid, and that they are compared against a trusted set of information, which would be our DHCP snooping database that was created during our DHCP snooping process. So IP ARP inspection is the command that you would use to configure dynamic ARP inspection, and it is a global configuration command, and it is configured per VLAN, much like DHCP snooping. You do also need to configure interface trust, a lot like with DHCP snooping, that for devices that have static IP addresses assigned, you can do IP ARP inspection trust, such that the check for whether it's a valid ARP or not will be completely bypassed on a trusted interface, so that the interface here where the router connects, you can trust that interface and say, I have a statically configured IP address on that interface where I know and trust that device, and that I will bypass my dynamic ARP inspection process. Awesome. So now let's go through the lab here. And I know we've got a lot of words here, but let's step through this one at a time and take a look at what we're going to do. So we're going to first go ahead and configure port security. That we've got two routers here, R1 and R2. We've got a switch in the middle, and we've got a DHCP server over here. So R1 is going to be a DHCP client. R2 is going to be a statically assigned IP address. Our network is the 10.1.2.0/24 network. And we're going to assign .5 to R2, and our DHCP server is going to be .1. We're actually not going to touch that guy. I've already configured the DHCP server over here. That we're just going to be on the switch and on the routers here to go ahead and ping around and see what happens when we configure these layer 2 security measures on the switch, and see what happens when we have violations, and also what it looks like when it's working appropriately. So first up, we're going to do port security. We're going to configure port security on fast 1/0/2 of switch 1. So on this interface that R1 is connected to, we're going to go ahead and configure port security. Now, I know these interface naming conventions are a little different than before. This is because I don't have the IP base or LAN base image for GNS3, that I needed to pull out my physical devices and go ahead and use my physical switch and routers available to go ahead and set up this lab here. So it's going to end up looking a little different on the console here as well than before, just because we're using a different console software. And that here, just as a quick note, that R2 is not actually a router per se. It is a layer 3 switch. That's why the naming convention for the interface is also in the same kind of switch naming convention here. But it will effectively work the same, because all we're doing is sourcing some packets from the MAC address there. Awesome. So let's first go ahead and configure port security and take a look at what's going to happen. Great, so we're over on switch 1 here. We're going to go enable and config T. And let's go to interface fast 1/0/2. And actually, let's do a do show run interface fast 1/0/2. Is that right now we are just an access port. This was a trunk at one point, so the encapsulation is set to .1Q, but it is just an access port right now in VLAN 1, and there's no additional configuration. So let's go ahead and configure port security. So if we go switch port, port security, and that's actually all we got to do, is now port security is enabled. Now if we do show port security, whoops, then we see that we have interface fast 102 with port security enabled. It is allowed one maximum MAC address, and that there is currently one MAC address there. So if I do show port security interface fast 102, then our last MAC address here was 000C8508, and it's on VLAN 1. And then we have port security enabled and is secure up, and the violation mode is shut down. Cool. So let's go on over to R1 here, right? And let's first enable, let's do a show interface fast 0/0, because that's the interface that's connected to our switch on the interface that we configured port security. And just take a quick look, is that we have the same MAC address here, the 000C8508D440. And that we have this information right here that you may or may not have paid attention to before. It is the burned in address. So the hardware MAC address that is on that interface, this is there because you can actually change the MAC address that is assigned to this interface and use a different MAC address and do spoofing in that manner. So just to show right now is that we can ping our default gateway, is that if I do a show IP interface brief, is I already have DHCP enabled on fast00, and that we have the address of 10.1.2.100, and that it is up, and that I can ping 10.1.2.1, our DHCP server, and that is successful. Now, what I want to do is I'll go config T and go to interface fast00, and let's set our MAC address to something else. Here it's going to use in the 4 dotted manner that Cisco usually uses. So we're going to do just 1211.1111.1111 for our R1, right? And that's our MAC address. Now let's go ahead and actually just take a look at what happened on our switch already. Is that we have right here port security to a level 2 error message here, P secure violation. Security violation occurred caused by MAC address 1211.111.111 on interface fast 102. And that the P secure violation, the port security violation error detected and is putting it into error disable state. That right now, if I go to show in status, that fast 102 is in error disable state. If I do show port security, I now have my violation count incremented to 1, and that current address count actually went down to 0 because that interface is disabled now. If I do a show port security interface fast 102, that port security is enabled and it is in secure shutdown status, and that the last source address was this guy, the one that actually caused the violation, and that the security violation count was incremented to 1. Now, to show what would happen here is let's go to config T and go to interface fast 102. Whoops. And let's do a no shut. And that actually, do I have port fast enabled on this port? I might not, so it's probably going to take us a few moments here for this to actually work. That if I go and check real quick of do show port security, that actually no, the current address count is 1 already. So if I do show port security address, this will list the secure addresses, and that we've got the configured MAC address here. And then let's go ahead and just do a no MAC address to get rid of that configuration here on R1. And then just like that, we have another port security violation because it sends out a gratuitous ARP saying my MAC address is now this, that this IP address now resides at my new MAC address, the 000C8508D440. Awesome. So now that's port security, and you can see kind of how that works. We could allow more than one MAC address here, and in fact, let's go ahead and do that real quick. Let's do switch port security maximum, and let's up this to 2. And then we got to do a shut, no shut, and bring that back up. And now, if we do a show port security, our max secure address count is up to 2. And if we take a look at this again, there we go. The current address count is up to 1. And then now we can actually go ahead and put our MAC address configuration back here, right? And give it the new MAC address because it's now going to go ahead and send out a gratuitous ARP. If we do a show port security, that our current address count is now incremented to 2. If I do a show port security address, is that now both of these MAC addresses show to live off of this interface, fast102, and that they are of type secure dynamic, where they are learned, they are secured, and that they are dynamic, and that they were learned dynamically. Awesome. So that's port security. Let's go ahead and disable port security. Let's do a no switch port security. Great. And then let's get rid of our MAC address configuration here. No MAC address. Awesome. And then now let's go ahead and take another look at our lab here. So that was part 1. So we went ahead and configured port security, and then we pinged the DHCP server and then changed the interface MAC and pinged again, and we reviewed the results. So that's 1 and 2 down here. So now let's move on to 3, 4, and 5. Is that first up, let's go ahead and configure DHCP snooping on switch 1, and we'll set only fast101 as a trusted interface. Actually, let me go ahead and clear some of this off here. There we go. Is that we're only going to set fast101 as our trusted interface for DHCP snooping. And we're going to renew the DHCP address from R1. And then we'll go ahead and take a look at what the DHCP snooping binding looks like on switch 1 and go from there as well. So let's go ahead and move on over to our console here again. Is it over on switch 1? We're going to go to fast101. Let's do a IP DHCP snooping trust. Now we haven't configured DHCP snooping yet, but we went ahead and just set our interface as trusted. And then let's go ahead and go exit, do IP DHCP snooping. Go ahead and enable that globally. And then do IP DHCP snooping and enable it on the VLAN. Great. So that's enabled now. Now if I do end, and if I go ahead and do show IP DHCP snoop, then we have here that there is a trusted interface, and that it does not have any rate limit. It's just showing us the configuration information, and that it is enabled on VLAN 1. And that if we do show IP DHCP snooping binding, that there are no bindings here. So let's go ahead and on this interface, let's remove the IP address and have it renew this. So we're going to go no IP address. And then let's do a do show IP interface brief. And that we now have an unassigned on fast00. And let's do IP address DHCP. So that might take it a few moments here to go ahead and send out that discover, and there it goes. It was assigned the IP address 10.2.100 with a 24-bit mask. If we go and check our switch here, is that now if we do a show IP DHCP snooping binding, is we now have a binding. is that we have our MAC address that is matched up to 10.1.2.100, and it took note of the lease time as well, and how it was learned, what VLAN it is, what interface that device lives off of as well. So that's how our DHCP snooping works. That let's go ahead and do this is we'll actually remove the interface trust. Let's go to config t interface fast 1/0/1. Let's do no IP DHCP snooping trust. Awesome. And then let's go ahead and go here and do again no IP address and release that address here. And then do IP address DHCP. Now let's just let that sit for a little while, right? Is that we went ahead and did this. It took it a little bit for that DHCP address to be assigned. So, we went ahead and set that for DHCP. If it does obtain an address, it should show us shortly here. Which, going back a little bit, it still hasn't gotten an address, and that the violation here for DHCP snooping is actually not logged. There's no traps sent, and it's just the frames are dropped. That the response frames here from the DHCP server are just being dropped, so we will never receive an IP address. That we need to go ahead and put our trust back on that interface. And then, now that that's trusted again, let's do a no IP address and do IP address DHCP, and then momentarily we should end up getting an IP address by DHCP. And there it is right there. Excellent. So let's take a look at our lab steps here one more time. Is that we now have DHCP snooping configured, and it is working. We confirmed it is with the trusted interface. So now let's go ahead and configure dynamic ARP inspection. Is that we will set only fast 101 as a trusted interface, because this .1 on the 10.1.2.1 address, that is statically assigned to our DHCP server. So I'll need to set this interface as a trusted interface for dynamic ARP inspection as well. And then we'll go ahead and ping that from R1. And then I'm also going to go over to R2 and try to ping the DHCP server as well and see what happens there. So let's go ahead and configure dynamic ARP inspection and set our trusted interface. This is going to be IP ARP inspection VLAN 1, and then let's go over to our interface fast 101 and do IP ARP inspection trust. Awesome. So now that that's there, let's go over to R1 and let's ping our DHCP server. And that is successful. We lost one because we had to ARP out, but that's no problem. That is successful here. Now let's go on over to R2 here. Let's go enable. Let's do a show IP interface brief. And like I said, this is actually a switch, so that's why we have so many interfaces, but our VLAN 1 interface is 10.1.2.5, and if I go ping 10.1.2.1 and enter, that is not working. And if you noticed up here, the icon changed for our switch, showing that there is some message showing there. If we go back here, we've got all of these errors happening. These log messages showing up of invalid ARPs and invalid ARP requests specifically. That this would be RES for a response if that was needed. That it is on fast 104 where R2 lives, right? And that it's showing us the MAC address and IP address that the ARP is claiming, and that it is not in the DHCP snooping database, so it is not allowing that ARP, and it is just dropping it. And that this type of log message is switch dynamic ARP inspection, a level 4 log message, and it is DHCP snooping deny. Now, interestingly enough, something to note is that if you have dynamic ARP inspection enabled without DHCP snooping enabled, which it does allow you to do that, but dynamic ARP inspection will deny everything because there are no entries in the DHCP snooping database, so it claims that all ARPs are invalid. So now that we've done that, let's go ahead and trust fast104, and then let's ping around and check the differences there. But actually, we can do a show IP ARP. That was a mistake. If we do a show IP ARP inspection, is that this shows us information about our configuration. DHCP drops, there have been 29. There have been 10 forwarded and 29 dropped as a whole. And then we can also do show IP ARP inspection interfaces. And it shows us our rate limit and our burst interval and what the trust state is for our interfaces. So let's go back to config T. I'll go interface fast104. And we're going to do IP ARP inspection trust. Awesome. And now that that's placed there, let's go back over to R2. And if we try and ping out, it is successful. It took a little long for the first one, but from there, it is successful. Awesome. So now that should show you how DHCP snooping and dynamic ARP inspection works, and also how port security works and how that's configured, and how you'll be able to check and confirm that as well. Awesome. Thanks so much for going through this with me. Just like the others, let's run through a couple of practice questions before we end off. First, if port security is enabled on a port and more than one MAC address appears as the source for frames coming into the interface, what will happen to the interface by default? So the key here is that we're talking by default, and that this is kind of a long-winded way of saying, what if you have more than one MAC and you have a port security violation? What is the default action? Will it be shut down? Well, that is the action. Is it that nothing, the offending frame will be dropped? That's not correct. It will enter error disable mode, or it will enter psecure violate mode. Now the answer here is C, is that it will enter error disable mode, where you as the admin generally need to go in and clear that by doing a shut no shut on the interface. And then finally, what will happen when a frame is received on an untrusted interface with dynamic ARP inspection, which does not match an entry in the DHCP snooping database? Is the frame dropped? Is the interface shut down? The interface enters error disable mode, or nothing will happen by default. As we just saw, the frame is dropped and that it does not go through, so our ARP will never be propagated onto the network. Now, I hope that this has been informative for you, and I'd like to thank you for viewing.
Wireless security. In this video, we're going to go over a brief overview of the history of security protocols used in wireless, specifically in Wi-Fi. And then we'll also take a look at WPA, Wi-Fi Protected Access, and WPA2, and the newly released WPA3. And then we'll also go through a brief lab going through on a Cisco wireless controller how to set up a new SSID and how to configure it for our best wireless security at the moment for WPA. So first up, let's do an overview of some wireless security. So WPA, Wireless Protected Access, was developed as an immediate replacement to WEP when it was found to be insecure. See, WEP stands for Wired Equivalent Privacy. WEP was found, and even known at the time, to be pretty insecure. It is vulnerable to many different types of attacks, and even particularly it is vulnerable to offline attacks, to decryption attacks. The WPA certification implements most of 802.11i. That is the specification that WPA certification states that your implementation has been certified to include all of the mandatory or most of the mandatory elements of 802.11i. And particularly for WPA, when that was released, it introduced TKIP, Temporal Key Integrity Protocol, for per packet keys. And this really combated a lot of the main security concerns for WEP
and changes what key is used to encrypt your packet on a per packet basis. So Wi-Fi certified devices, and Wi-Fi, mind you, is an alliance. There's the Wi-Fi Alliance, and they certify devices to be compliant with different standardizations of, and specifically here, 802.11i is for WPA and WPA2. That WPA2 is specifically, it implements all mandatory elements of 802.11i. And that is that WPA2 particularly mandates support for CCMP. And we're going to talk about that in the next slide here as to what that is. And it's an AES-based encryption protocol. You may remember AES when we talked about VPNs, that AES is the Advanced Encryption Standard. CCMP is an AES-based encryption protocol. And your wireless security, just as a note here, it is particularly important because anyone in range can listen in to the transmission. Think about it, that rather than using a physical wire as your transmission medium, you're using the air, the space around you, the electromagnetic waves that are broadcast out. If anyone is within listening distance of that transmission, they can collect that data and then save it to go and start decrypting that later and find your sensitive information. You can do a capture immediately, that where we would go ahead and lock our switches behind closed doors and make sure we have good cable management up in the ceiling where it's not easily accessible, and that our switches ensure that the traffic doesn't go to the wrong devices and is only directed to the device that it's intended. With wireless, any device in range can listen in on that transmission and can potentially gain the information that was being transmitted. So let's compare a couple of these wireless security protocols. So WPA, it implements TKIP for message integrity checks, and it's stronger than the cyclic redundancy check, the CRC that's used in WEP. That's where TKIP really improved on, WPA really improved on WEP, is that TKIP is much stronger than CRC for integrity checks. And better message integrity protocols existed at the time when WPA was released, but generally they were too computationally expensive for the network interface cards. That's specifically not the access point, the wireless access point, but the interface cards, the NICs that were used on the devices on our laptops and such, that these protocols were generally too computationally expensive to be able to maintain the necessary amount of throughput, and so TKIP was used rather than some other more secure or better integrity protocols. And where CRC was problematic is that it allowed for your transmissions, your frames, to potentially be modified and retransmitted, and the station and the access point were none the wiser. And just as a quick note, STA here for station, that's your client, and AP, this is your wireless access point. And that this diagram down here is illustrating the four-way handshake that WPA and WPA2 use in order to verify that you have the correct pre-shared key, that you are actually allowed to connect to this network and begin a security association with the access point so that you can encrypt data being transmitted between. Now, WPA2 does improve on TKIP, and as I said, it uses CCMP. Now, CCMP, this stands for counter mode, that's the first C. Cipher block chaining, and that's the second C. Message authentication code, that's the M protocol. And that is CBCMAC, is the cipher block chaining message authentication code section of CCMP, and that specifically CCMP is the counter mode of CBCMAC. And that is even still stronger than TKIP. And like I said, both WPA and WPA2 use a four-way handshake to confirm the correct pre-shared key is in possession on both sides, and it does this without ever transmitting the actual pre-shared key. I would be familiar with the directions and the steps here in the four-way handshake, that the A nonce is transmitted from the access point to the station, which is the client, and then the station constructs the pre-shared, the PTK here, and the S nonce plus MIC is transported back to the access point, and then the access point constructs its PTK and transmits that back, and as long as everything's all in agreement, then there's an acknowledgement sent back, and that we now know we have the correct pre-shared key on both sides, and the actual key itself was never transmitted, so it could not be compromised or has a much lower likelihood of being compromised. Both WPA and WPA2 also support EAP extensions, our extensible authentication protocol, which is also known as 802.1x. This is known as the enterprise mode. That when you see WPA or WPA2 personal, that is for PSK, pre-shared key, and WPA or WPA2 enterprise is the EAP extensions implementation, or the 802.1x implementation, where typically you would use something like Radius or LDAP for authentication, potentially using certificate-based authentication with WPA Enterprise or WPA2 Enterprise. Now, both the personal and enterprise mode use the same 128-bit encryption. This is something that I would take note of, is that for WPA and WPA2, both enterprise and personal mode for both of them use the same 128-bit encryption. Now let's talk a little bit about WPA3 and how that differences with WPA2. First up, what I had noted, where we had the same 128-bit encryption for personal and enterprise with WPA and WPA2, WPA3 requires 192-bit equivalent encryption for enterprise mode, whereas 128-bit is still okay for personal mode. Now, WPA3, the other big change that's here is that it replaces the PSK four-way handshake with a new protocol called the simultaneous authentication of equals, typically stated as SAE. And there's a diagram showing the SAE protocol overview here and the steps that are involved. I wouldn't necessarily know the individual steps that are involved here, but you can see that SAE kind of has its own bit here at the top, and then it does a PSK, the four-way handshake, here at the bottom. It sort of just adds on to the PSK four-way handshake with its SAE, the simultaneous authentication of equals. And as a quick note, it includes forward secrecy to prevent offline decryption attacks. This was something that WPA2 was vulnerable to, that you could record the transmissions that were there and be able to brute force them offline and decrypt those. Excellent. So that's the main overview between WPA, WPA2, and WPA3. WPA3, as a quick note, this was released in June of 2018. The actual certification for it was the devices are still being created and going through certification process, so that's going to take some time before that actually comes out. So now let's jump into our lab here and take a look at what we're going to do with that. It's going to be a pretty simple lab. We're going to jump into a wireless controller, and we will add a dynamic interface using VLAN 50. And we will configure an SSID to use the new virtual interface, and we will set the SSID to use WPA2 PSK or WPA2 personal, and I'm going to set this actually to not broadcast, and I'll show you where that option is, but I will enable the SSID. This is because this wireless controller is actually in a production environment, and I don't want to have a new SSID just randomly pop up for people. The changes that we're making here will not affect the existing SSIDs in the event that you are managing a production network, that if you are adding a new SSID, that should not have any effect to the existing ones unless you have a large configuration problem of overlapping VLANs or IP addresses or things of that sort. And finally, we're going to add the SSID to an AP group, and I will show you what that means here shortly when we go into the lab. Alrighty, so let's go over to our wireless controller here. So here we are on a 5500 series wireless controller. So first up, let's go ahead and add our new dynamic interface using VLAN 50. So we're going to go over to the controller tab, and then we're going to go over to our interfaces section. And then we're going to do a new interface here in the upper right. Our interface name, I'm going to call this BJ Train Lab. And our VLAN ID is going to be 50. Awesome. And then we're here in our interface configuration section. So the port number, the primary port that we want this to use, which is the physical port on the wireless controller that this interface, this dynamic interface will use. So where this virtual interface, the VLAN 50 interface, what physical port that is mapped to, I'm going to set that to port 1, and we're not going to have a backup port. This is going to be port 0. Our VLAN identifier is 50. Let's do an IP address of 10.50.0.2. And net mask will be a /24. And our gateway, let's do 10.50.0.1. I do not actually have this configured on any router or switch at the moment, so this SSID would not be functional, but this is what we're going to set up here on our wireless controller. You would need to do the appropriate VLAN configuration at the layer 2 and layer 3 configuration on your router in order to get your new SSID to actually work. And we're not going to use DHCP relay here or DHCP proxy on this interface. I'm going to leave it at just layer 2 DHCP, that the discovers will end up hitting a DHCP server that is inside that layer 2 domain. And everything else here we're going to go ahead and leave the same for right now, so let's go ahead and apply. And there we go. So now if we go back over to our interfaces, we see we now have this new interface, BJ Train Lab. So let's go ahead and create our SSID using the new virtual interface. So we're going to create new and click go. Profile name, this can be arbitrary here for the moment, BJ Train Lab. And then I'm going to do the same thing for the SSID name. And now we're here in the WLAN configuration section. So like I said, I'm going to uncheck the broadcast SSID checkbox here, but I am going to enable the SSID. And then here we need to set what interface or interface group that this SSID is a member of. This is where we choose our new virtual interface that we created, the BJ Train Lab interface. And if we go over here to our security tab, we see that at the moment we already have WPA and WPA2 layer 2 security selected. And then here in this section is where we select specifically that we want WPA2 to be used and not WPA. And then here we have it as WPA2 Enterprise with 802.1x enabled at the moment. We're going to disable that and use pre-shared key. And that's where it gives us the PSK down here where we can type that in. I've created my pre-shared key, and that's actually all we need to do here. We could add some other types of security, like layer 3 security for a splash page or a captive portal that we end up getting where we need to log into. Or if we had 802.1x selected, we can configure our authentication servers here with LDAP or Radius here in our AAA servers section. We can also set our QoS policies and do policy mapping with ACLs on our wireless controller here, but we're not going to get into any of that right now. We're just creating a new SSID that is WPA2 only using PSK authentication. We'll go ahead and click apply. Excellent. So now that that's been created, we go back over here to our WLANs. We see we have BJ Train Lab, our new SSID created there. And now let's go over to our AP groups. So our AP groups, an AP group is a group of access points where you have all of these WLANs, right? All of these SSIDs, but you don't want to broadcast all of these SSIDs from all of your access points. So you can group your access points into various groups, typically by location. Here we have Aurora, Detroit, Jacksonville, Montreal, and inside each of these groups, we have our access points at that location added to the group, and then what SSIDs we want to broadcast in that group. So we're going to go ahead and go over to our AP groups, and actually let's broadcast this one out of the Detroit AP group. And if we go add new to the WLANs, do BJ Train Lab as the interface and BJ Train Lab as the SSID, and go add. And there we go, and that's all you got to do. Then in a few moments, once the provisioning takes effect through your CapWAP to your access points, then you'll start seeing that SSID pop up if you do have it set to broadcast, which we do not. So, excellent. That was our lab here. Let's go ahead and jump back over to our presentation and run through a couple of practice questions before we end off. First, what is the name of the authentication protocol used in WPA3? Is it pre-shared key, asynchronous authentication of equals, simultaneous authentication of equals, or temporal key integrity protocol? Here it was SAE, our simultaneous authentication of equals. And finally, what message integrity check protocol is used by WPA2? Is it TKIP, CRC, CBC MAC, or SAE? Now SAE, as we just saw, was the handshake that is used for WPA3, TKIP is for WPA, CRC is for WEP, so the answer here would be C, CBC MAC, or CCMP would also be an acceptable answer. Now I hope that this has been informative for you, and I'd like to thank you for viewing. Network automation. In this video, we're going to talk a little bit about how automation will change network management and its impact, how we currently manage the network in the more traditional sense, and what different automation technologies can do for us. And then specifically, we're going to go through a little bit of Cisco's DNA Center and talk about what that is and how that increases network automation and changes the way that we manage our networks. So first, let's talk about traditional box-by-box management. So generally, we still go to each individual network device, right? Is that you've got, say, like a switch here, and it's connected over to a router, and that might be connected to another switch, and that's connected to another router, and then maybe that's connected to, a firewall. And I can't really draw a firewall here, but anyway, you get the idea. A firewall, and that's connected over to the internet, right? And that in order to make changes here, in order to say that, maybe we've got a handful of computers coming off of here, and we've got a handful of machines coming off of here, and then let's say we've also got, a wireless access point coming off of here, and that we've also got a wireless access point coming off of here, and that, say we've got, door locks or security cameras, or we are now implementing retinal scanners at each desk or something like that, and that you need to go ahead and set up a new network for these devices, a new VLAN or a new security context, a new security level for these devices. What do you need to do? You actually need to go to each of these individual devices and make that change. Is that you need to add a VLAN to your switches. You need to add a virtual interface or a sub interface to your routers. You need to add a new VLAN or security level to your firewall. And all of these devices need to be touched individually. I mean, in a 5-device network like this, that's not really very big. But imagine that you had a 500-device network. That this becomes a huge administrative effort problem, that this is just not scalable, that sure, you can throw more people at it, you could just make your network team larger and larger to go ahead and handle these larger groups of devices, but you're going to still end up spending a lot of your time in doing this. And beyond anything else as well, it's very error prone. That when you're actually there at the CLI and typing in commands, there's a lot of chance that you can make a typo. That say you're putting in an ACL and that you accidentally capitalize a letter in one spot and you don't in the other. Well, that ACL doesn't have effect anymore. Is that you now don't actually have the same ACL reference because one is capitalized and the other is not. And unless you're writing out your configuration on Notepad or something and then pasting that into each of your devices, which a lot of times is not even feasible because of the different configuration that's required on many of your devices, then it's still very error prone. And I remember seeing something like at least 40%, if not more, that's the number of network outages that are caused by IT people and by errors made in configuration. That really a lot of our troubles are self-induced, and I'm sure you've encountered this as well before. You go to make a change, say you're updating your OSPF here on your device, and it's something that you did not think was going to cause a full neighbor's reset, and it does. And all of your neighbor relationships are gone. All of your routes are gone, so you now have a network outage, at least for a short period of time while all the neighbor relationships are rebuilt, and then everything comes back up because you have all your routes back. Or over here, that you didn't realize that something that you were doing, or you made a typo, and you accidentally block all the traffic coming in on the interface. Well, at least that business unit here that comes off of that interface, or perhaps it was this interface and that half of your company is now down and you need to physically go over there and reset the device because you don't have management access anymore. These things happen. It's natural to make errors, and it's okay, but with that, it's just interesting to know that a lot of our network troubles are caused by ourselves. Even when you have really good, really solid change management processes in place, still a lot of errors are made and cause some problems for us. So this is just where our traditional management kind of has a failure, is that there's a scalability problem of having to touch every box when you want to make a change, and that there's also a planning issue. The fact that you do need to touch every box, and that any change you make to the network in deploying a new application, deploying voice over IP, now you need to add quality of service to every one of your hops, every one of your devices, or you need to do OUI filtering for your LLDP med for sending your voice VLAN to your individual devices and things of that sort, that this is a large change, a lot of boxes need to be touched, and that this is a scalability issue with traditional box-by-box management. So continuing a little further, in traditional management, like we said, that devices are managed manually and individually and possibly by the switch port IP or VLAN. It's just not scalable. That once you hit a certain number of devices, too much of your network engineer's time is spent managing day-to-day tasks on these devices, and that you're not adding any real business value to your corporation or to your organization, that you're just there doing maintenance. You are there as a body who happens to know how to type in commands, and that's just not the way that your knowledge, your expertise should be used, that you really should be adding more value to the business than that. And that typically inter-device communication is managed at the firewall or router via ACLs with our traditional device management. Now, how do we migrate into automation and network automation? Well, Cisco generally breaks this out into 3 phases. And the first phase is the configuration phase, where your syntax, your line-to-line syntax at the command line is abstracted. Your configuration is still done box by box, but you may have a configuration automation tool that allows you to set a configuration, and it will give you either a configuration to paste into the device, or it will go ahead and push it out for you directly. And that you're still setting this box by box individually, but a lot of the problem with it being error prone is now removed because that syntax is abstracted, and that you are no longer having to run the risk of making a typo and causing everything to just not work. And then the next step here would be at the provision phase. And at this phase, this is where you start viewing the network as a whole. That you're not really looking at individual box by box configuration and saying we need to set QoS here and on that interface right there, and that's going to have to route over here, but under certain circumstances it might come over here, and we need to have the QoS set up here on that interface. That you're starting to look at the network as a whole, to have your units of your network and to configure that unit to do certain things. And this starts with simple processes that you're going to go ahead and configure your VLANs out across, or your routing out across. Your OSPF domain will all be provisioned as a whole. And that there are certain tools available for this, which we'll talk about in a later video, that you can go ahead and use for configuration management and to be able to start configuring your network and looking at it as one whole unit instead of a bunch of individual little boxes. And as well, this is really between the provision and the program phase. This is really where Cisco DNA Center lives. And we'll talk about that in the coming slides, that you can view your network as a whole, and that you can also have APIs where applications do directly control the network to achieve the requirements. If you are in a large enough enterprise or in a company that does a lot of developer operations, that you can have internal applications that will go and provision different network services for your developers automatically. It can directly interact with your controller and be able to apply certain policies for new applications that are coming into play. I know it can be a little hard to visualize that, especially if you're used to the traditional device management where it's box by box and that you're having to go to the command line and understand exactly what's happening at that device. But you'll see soon here, and as you do some more reading, to understand how this really takes place. So that's really traditional device management and how we migrate into a fully automated network. Now let's talk about Cisco's newest software-defined network controller, and that's really what DNA Center is. It is an SDN controller. And let's talk about what DNA is. DNA is the digital network architecture. Now this is a bit of a marketing term coined by Cisco, and really it's their next generation of software-defined networking. That devices that are DNA compatible are devices that are compatible with DNA Center. That previous to this, and it's a little bit of a different solution, is the Cisco ACI. You may have seen this before. It's the application-centric infrastructure. That's another term coined by Cisco for software-defined networking, and that the controller for this was the APIC EM. And the next generation of this, though, is Cisco DNA Center, and it adds a lot of new features and has a lot of new functionalities that APIC and ACI just did not have. So with DNA, devices are identified on your network with ICE, the Identity Services Engine. That's another Cisco product, very powerful identity service software that will allow you to identify devices and be able to control their identity and use it as an authentication server and integrate with your existing identity service, be it a directory of some sort for Active Directory or Novell or things of that sort, that ICE integrates and applies this to your network. And devices can be placed into groups using security group tags. Remember this, that's an SGT. We'll reference that a little more later. So this is a lot like a security group in your directory if you're placing a user or a computer in your directory software like Active Directory with a security group membership. A security group tag is a lot like that, but for ICE. And the physical network is then segregated into virtual networks. And this will be abbreviated as VNs in the future here. And that the virtual networks are really akin to VLANs. But this is just a more abstracted construct of virtual network that it exists as an overlay network to your software-defined network, your underlay, your physical architecture, your fabric. And we'll talk a little bit more about that in future videos here as to what the overlay and underlay network really are and how that applies. And that the security group tags, they are granted certain access to and between virtual networks using contracts and policies. That, just as a note here, as far as DNA Center is concerned, a policy is just an application of contracts. You create contracts, which are really like these access control entries, and then you apply contracts to policies, which are really like your access control list, but are a little more flexible than just a regular ACL that we would create at the command line. And this figure here I took from Cisco's presentation on DNA Center, that before, in our traditional device management, VLAN and IP address based for our access controlling, and that we create IP-based access control lists for access policy, and that we deal with policy violations and errors manually for certain points when devices are accessing things that they shouldn't, or are in some way moved and now violating their access policy. That if you have a ACL that is tied to a VLAN that's an access on a single port, if somebody moves that device to a new port, it may not be on the same VLAN now, and that we now might have a policy violation for that device or that type of device because it's now sitting on a new VLAN. And in the new network architecture and the digital network architecture, we don't run into that kind of problem because we are applying our security group tags and our access to virtual networks based on the identity of the device. That there is no VLAN or subnet dependency for segmentation and access control. That it's controlled by your security group tags and your virtual networks, your policies that are applied, and those follow your device. The policy follows the identity, and we define one consistent policy for the devices, and that it follows those devices. So next up, we're going to go a little bit through Cisco DNA Center. I wanted to give you some screenshots to understand what the interface here looks like. So now that we have an understanding a little bit more about how we manage access control in Cisco DNA, let's see how that translates into a more practical sense. So here's a screenshot out of Cisco DNA Center. We are over in our policy section, and that we're in our virtual network, and we're setting which SGTs, which security group tags, or they also call them scalable groups, apply and have access to a virtual network. So we're in our default virtual network here, and we have several different virtual networks to choose from, and we have these SGTs, that these are our SGTs, our Internet of Things for lighting, and our Internet of Things for the RMO. And then over here we also have a bunch of different security group tags as well, and that we can grant our security group tags access to virtual networks in this fashion. And then up here, I want to make note that we also have access to the group-based access control, to have one group have access to another group, regardless of what virtual network it's in, and we can specify exactly what type of access. Now, this isn't to say we don't have access to the IP-based access control. We do, or even the application-based access control. We have access to that as well. And something I wanted to mention here briefly, and you may not be as caught up with this as I was, but assurance, as far as what this actually means, and Cisco DNA Center is really big on assurance and the assurance center. That what that is the amount of auditing and information available to assure you that your policies are actually working in the fashion you expect, to where it will give details and reports to show that this is actually what's going on. Now, as far as the group-based access control, over here we are in that section. This gives a whole matrix, right? And there's a bunch of default defined policies as well. And that in this particular example, we've got 11,000 policies here in our group-based access control. And what this is saying from one security group tag to another. So we have the IoT camera SGT and the auditor's SGT. And that we're creating a custom policy. And that this contract here, we can go ahead and create and assign a contract, and that we are applying this policy to where here the name of this contract is block malware, and that this contract is being applied in this policy. And here's what this contract does is it is, permit deny, and what the application is, the protocol, source and destination, the port, and whether we're logging or not. That these are a lot like access control entries, you remember from ACLs, and that the contract is like an ACL, and that we apply an ACL with a policy, or we apply a contract with a policy. And we can just do a straight deny policy or a permit policy to permit traffic between two different security group tags. And remember, these security group tags are following our device because that's how they are identified by ICE. When they plug in the device, it is identified by ICE, and that our DNA, our digital network architecture, is then applying policies to that device. Awesome. Now, I know that this has been a little abstract and your head might not be quite wrapped around it yet, and that's okay. We're going to talk more about software-defined networking and automation in the coming videos here. But before we end off, let's just go over a couple of practice questions. First up, what concept in Cisco's DNA Center replaces VLANs? Security group tags, policies, virtual networks, or contracts? And the answer here, we mentioned that it is very akin to VLANs. It is C, virtual networks. And then finally, how are identities grouped to provide similar security policies to devices of the same type? Is it using security group tags, using virtual networks? Is it with contracts, or with the digital network architecture? And we had talked that the thing that is very similar to security group membership are security group tags, and the answer here would be A. I hope that this has been informative for you, and I'd like to thank you for viewing. SDN architectures. In this video, we're going to talk about the difference between a controller-based network and how traditional networks operate, and also go over some terminology used with software-defined networks like the overlay and underlay network, and take a look and understand what that actually means. Now, with software-defined networking, this is a really hot topic now, of course, and it has been for a few years, and it can be a little difficult to weed through a lot of the marketing buzzwords and propaganda, for lack of a better word, that's out there from the various vendors, and try and understand really what this actually means and the practical applications it has, and where this ends up changing things from an architecture perspective. So with that, let's go ahead and jump in and talk a little bit about how current networks operate and what a controller-based network ends up changing for us. So first, let's talk about the difference between the data plane and the control plane on various devices. So on a router or a switch or other network devices, you have three distinct planes. That you have the management plane, which we're not covering really here, and you have the data plane and the control plane. That really these are meant to be software planes where different processing happens, either hardware level ASIC processing, application specific integrated circuit processing, or your software processing where your CPU actually spends CPU cycles and running through software to process certain things. So your control plane, this is where your control traffic happens. For a router, this would be where OSPF operates, or where CDP operates. CDP would actually be in your management plane, but your control plane are things that have to be processed by the CPU. So for routing protocols or packets originating from the device, for a switch, this might end up being things revolving around your MAC address tables and your VLANs and setting those VLANs on the interfaces, that those are all control plane operations, that the way you would do that is through the CLI or SNMP or APIs, and that occurs on the management plane. But the other information of actually setting it, or the processing that the CPU has to do for any packets coming in, if it needs to do CPU processing, then that is happening at the control plane. Your data plane is where your forwarding table is. That this is where your ASICs live, your application-specific integrated circuits. This is where traffic being actually forwarded through your device ends up going through the data plane. And these two, the data plane and control plane, are really the operations that are relevant to our SDN conversation here. That, as we see in the diagram here, your OSPF hello timers are processed by your control plane. Your neighbor tables and link state database, that's all processed by the control plane, and that'll all get put into the routing table that exists in the control plane, which then gets diluted into a forwarding table, and that forwarding table exists in the data plane. And this is where CEF, Cisco Express Forwarding, exists, is down in the data plane. But if you need to do software switching, then that packet is forwarded up into the control plane, and your software switching happens up there if it cannot do hardware switching down in the data plane. So that's how regular devices work, right? Is that you've got these three distinct planes in each individual device: your management plane, where we manage the device; your control plane, where CPU processing happens; and your data plane, where hardware switching and ASIC-based forwarding ends up happening. Now step in controller-based networks. Now controller-based networks end up taking your control plane and move it to a central control plane. That your controller is actually just a centralized control plane. And the devices are only act really as distributed data planes, that they do the forwarding, and you are doing the centralized CPU processing on the controller, and the individual devices still utilize their management planes, because you do need to be able to manage them with the controller or be able to query them with SNMP to the individual devices, which you can also do from the controller, typically, as you would see in ACI or DNA Center, that you can get information about your individual devices from your controller, but your management plane is still active on your individual devices. It's your control plane that is not active on these devices, that function has been offloaded to your SDN controller, right? So let's talk about some of the other terminology that you'll see with SDN. The first up, network fabric. So network fabric can be a little confusing. It's used in slightly different ways depending on which documentation you're looking at. Generally, the network fabric consists of the physical connections between networking devices. That this usually does not include connections to endpoint devices like your servers or your workstations or your access points, but physical connections between networking devices. That it generally comes from the idea that fabrics, right, are these interwoven threads, and that you end up having just this thread of interwoven bits that look like a fabric, right? And that you can kind of take a look here at, this is a image depicting Facebook's newer 3-layer fat tree topology, also called their network fabric, their fat tree fabric, that these interlacing lines here that are all the network connections in their data center node looks like a fabric, and it all interweaves like a fabric, and that's where that term ends up coming from, is that this is definitively, say if you have a router here and a router here and a connection there, this would be a fabric connection, or a switch to a switch. this would be a fabric connection. If you have a switch to a workstation, this would not be considered a fabric connection because that is not part of your networking fabric. This is an endpoint connection, that it's only your networking devices connections that are considered to be part of the network fabric. And you would see that in your controller-based networks, in the terminology used in those interfaces and in the APIs, that it is looking for fabric connections, and those fabric connections are connections between your network devices. Awesome. So let's talk about what an underlay network and overlay network is. You may have heard this before, but let's go ahead and clarify what this really is. So we have here our underlay and overlay network. Our overlay network is a virtual network topology that is created from our underlay. So these two terms are directly related to each other, right? Is that your underlay network is similar to your network fabric, and it is the logical or physical connections between your network devices. And it's typically also the management network for the software-defined network. So you have here in the blue all of these physical connections here, but then after some perhaps VLANing or spanning tree blocking or a MPLS, what have you, perhaps since these are virtual switches here, that you have a layer 2 MPLS going across, a VPLS. And that to these virtual switches, as far as they're concerned, they are directly connected here. So that would be the overlay network. And that leads us right into the next slide here, that the overlay network is the virtual network topology that is created for client traffic. And the network is any logical topology that is created from the physical devices. So an overlay network and underlay network really don't have anything to do with software-defined networking in and of itself. We've been using overlay networks for a long time now. VLANs are an overlay network on top of our physical network infrastructure, that your VLAN may not actually span your entire physical network, and that it is a virtual LAN. It is an overlay network on top of your physical topology. But generally what we're talking about here is more of in a software-defined network context for the CCNA exam here, and that your overlay network would be the virtual network topology created for your client traffic. Awesome. Now, I know this one was pretty quick. Let's run through just a couple of practice questions before we end off here. First up, which network device plane handles responding to pings? Now, this would be traffic that is destined to or originating from the device itself, and that is handled by C, the control plane. And finally, which plane is offloaded to a controller in a controller-based software-defined network? And it's really a dead giveaway from the name that it is the control plane A that is offloaded to a controller in a controller-based software-defined network. I hope that this has been informative for you, and I'd like to thank you for viewing. REST API characteristics. In this video, we're going to go over what an API is, and also how REST works and its characteristics, and then also look into how to interpret a very common method of notating the data that is transferred with a REST API, and why this ends up being useful for us as network engineers, that this seems much more like a programming thing, and honestly the line between a network engineer and a programmer is being blurred somewhat when we're working with controller-based architectures and software-defined networks, that most of the controllers have APIs built into them, and the controllers generally communicate with the network devices via an API, and these methods of REST are what it generally uses to do that communication. So it's important to be aware of what this is and how you might read the information and to be able to recognize the information when you do see it. So first up, let's talk about APIs. What is an API? It is an application programming interface. As we say here, an API is a control interface created to allow one application to communicate with another. That this is a interface that is generally command line, it is text-based, and it is created so that one application can easily access another to either put information, to write information, or to get information about the system or about a specific device. If I want to poll something for information like SNMP, that our network management server, it pulls information from the SNMP agent, and that could be an API. That is an API for SNMP for it to gather that information. And software-defined network APIs allow for programmatic access to the controller's functions. That Meraki is a very common SDN solution, and it's more of a cloud-controlled, centralized controller architecture, more than it is SDN, but it does have some SDN qualities about it. And the controller for Meraki, the cloud controller, does have API available to where you can go ahead and write code. You can write applications in whichever language that you would most prefer and be able to access a lot of features of the Meraki controller. You can make changes to your network. You can gather information about your network. This way you can make on-the-fly changes that don't require any kind of human intervention. That you'll create applications that can go ahead and make changes to your network. If a certain circumstance comes to be, or if a end user ends up plugging in a specific device and you find that showing up in your clients list, which your API has now pulled, then you can make some change to the network. That this is just a small example, of course, that you can use that information to do a wide range of tasks. And the most common API implementation method is through REST. And that is the representational state transfer. And these APIs, they are called RESTful when they comply with the REST style, the REST architectural style. They are called RESTful APIs. Now, what is a REST API, or representational state transfer? Is that REST APIs provide functions for CRUD, C-R-U-D, to interact with an application. And more than that, it is the architectural style of APIs that was developed back in the early 2000s and late 90s, that this is what the web is really built on, right? Is that one of the major points of the REST API is that it is stateless. And what does that really mean? It means that between client queries, between sending an HTTP query or an HTTP message to the server and getting some response, be it that you're writing something to the server and get an OK back, or you're sending a GET request to the server and you're getting some application data back, that between those queries, nothing is cached on the server side. It is not keeping anything about the client on the server side. That everything that is needed in order to process that request is included with this one request, which would also stand for the server's response to the client. That everything that is needed in order to process that response from the server is included with that response. So it's a real quick action-reaction, that there's nothing else that we need in between, that you don't need to store information and then use that in your next request. You could, if you wanted to gather information about a device and then request more information about that device, then you may need to parse the response from the server, gather that information you're looking for, and then send another request to the server asking about that information. So CRUD, C-R-U-D, what does this mean? That is create, read, update, and delete. And this is implemented with the HTTP verbs post, get, put, and delete. Now, might be familiar with this, that when you do operations on the internet, when you go and visit a website, you are generally doing one of these operations with HTTP or HTTPS. They falls into the same way, just over TLS instead of unencrypted. So your GET operation, that is your standard, I'm requesting a URL and it is sending back the information. If you are visiting a website, you are putting a GET request to the web server and it is responding with the content of that website. If you are submitting a form, or if you are uploading a picture, a lot of times this is implemented with a post, that this is a create request, or it might be a put if you are updating something, that a put is to update an existing URI or an existing document on the web server, and post is to create a new document, a new picture, a new anything on the server, that you would do a post. And if you're submitting a web form, that may also be sending with a post. So the status code that you're going to end up getting back, here's a example of the client-side submission of a GET request to api.github.com. This is in Linux, and that they are doing this with curl, C-U-R-L, and that we are sending application type or content type application JSON that is JavaScript object notation. We're going to talk more about that in a couple slides here. And we are sending this to https://api.github.com. And we are doing verbose output here. And we see the initial TLS negotiation here to where we are getting the server certificate and verifying, we're connecting, etc. And then we have the connection open and we are doing our GET request to our host. We are sending our user agent along with our GET request in our HTTP header so that the server knows what kind of user agent that is submitting the request. We are accepting anything back, and we are requesting the response to be in JSON type formatting or JSON type encoding. I did not include the server response here, but the server does end up responding here with information about other queries that we can do to api.github.com, is that it ends up responding with a list of options saying here are potential queries you can do to api.github.com. And this isn't really needed here, but where this would be beneficial is if you are submitting a query to the REST API that is on the Cisco DNA Center, or to Meraki, or to the ACI, or APIC EM as the controller for ACI, that you can write scripts and write programs to interact with these controllers. And the method by which you'll be interacting is through an API, and generally they have a REST API, a RESTful API. All right, so let's talk about what goes into a REST API request. It consists of 4 parts: the endpoint, the method, the headers, and the data and body. And we had already looked at a couple of parts of this. The method is the CRUD, right? The post, get, put, delete, or create, read, update, and delete. And the endpoint is the URL that the request is sent to. In the previous slide, we were just sending to api.github.com, and this would be the root endpoint to some longer endpoint. If you were doing api.github.com/users/a username, generally having a colon in the beginning there, that means it is a variable and could be something different, a specific username perhaps, /repos. This would be the URL that we would send a GET request to list out the repositories on GitHub for a specific username. And that the root endpoint here would be api.github.com, and the path would be users the username repos. And the HTTP header are property value pairs separated by a colon. And we'll go over that a little bit more in a bit here, but this is used for a lot of purposes. Like you can include credentials or metadata about the data in our body. And let's just go back one slide that we can see here. These are the HTTP headers. We've got key value separated by a colon in the middle, that these are our HTTP headers here. And we can see the content type. We are requesting content type application/JSON. And the arrows here, the carets going to the right, that it indicates that it is information that was sent to the server. If the caret was going the other way, then to the left, that is information coming back to the client from the server. And this is just the notation for CURL in this distribution of Linux, that it could look very different depending on what application you're using to send the API request here. And the common data types are form-URL encoded and application/JSON. We're going to talk about both of those in just a moment here. And speaking of that the www-form-URL encoded, that's really the fuller name here, and it's I believe X www-form-URL encoded and JSON. That these are two really common ways that you're going to see the data being encoded. The URL encoded, this is when you see your keys and values up in your URL. That if you've ever submitted a form or gone to a website and you look up in the URL address bar and you see some of these values here, right, where you've got something equals something, ampersand, something equals something, that is form URL encoded data type being sent to the server, that it is actually an API, that you are sending some data with your state over to the server so that it can send the appropriate response back. And the data in the form URL encoded is plainly visible in the key equals value format in the URL requested. Now, JSON, JavaScript object notation, that encoding is stored in the body or the data section of the REST request. So in the body of the request that is sent, that is not in the URL, that will send JavaScript object notation information. And we're going to go over that in the next slide here of what that notation looks like and how to read that. That JSON structure is very similar to HTTP headers in that it is key value pairs separated by a colon. And I want you to keep that in mind when we go to the next slide here, that the notation opens with a curly bracket. All right, that a curly bracket opens an object, and that it consists here of key, colon, value. And then there are commas separating each of those in a object. And that our object can have many keys and values. Our object can also include objects, right? So there is this sub-object here, that this is a JSON notation for describing a squad of superheroes that live in Metro City. So our members here is actually an array. And an array is an object that has several values within it. So this is an array of objects. So we do that with a square bracket. And within the square bracket, we opened another object here, and that object is a person. It is Molecule Man. He's age 29. Secret identity is Dan Jukes. He has an array of powers, which is 3 different values: radiation resistance, comma, turning tiny, comma, radiation blast. And then we close that array. And that object for Molecule Man is now closed. We do a comma. We have another object here, Madame Uppercut. and that she is 39. Secret Identity Jane Wilson also has an array of 3 powers: million-ton punch, damage resistance, superhuman reflexes, and that array is now closed. Madame Uppercut Object is now closed, and the array of members is now closed, and then our object for the superhero squad is now also closed. That's how you read this. I understand if you have 0 experience with any kind of programming, this might feel really foreign to you. But this is something that you will need to know, that there is on the exam topics for CCNA interpreting JSON, that you'll need to understand that information is written in this format. I would review this slide a couple times if you need to. Although if you have some experience in programming, then you probably won't need to. That this will feel very similar to other work that you've done before. Alrighty, thanks for going through this with me. Just like the others, let's run through a couple of practice questions before we end off. First up, which HTTP verb would be used to retrieve information from an API? Is it the post, put, get, or delete? And remember, to retrieve would be to read information. And from CRUD, create, read, update, and delete, the read would translate to the HTTP verb get. That our answer here would be C, get. And finally, and this one's a bit longer here, in this excerpt from an ACI API JSON query response, what is the OSPF hello interval used in the default OSPF policy? This is an interesting thing here, that we can go over what an actual response from the application-centric infrastructure APIC EM, the controller, actually looks like. That when we sent this query for OSPF information, or for routing protocol information, that we've got things here for the control plane BGP configuration. And, well, our question here was about OSPF, so we don't really need that. We can jump down to the next object here and look at the OSPF policies. Now, within the OSPF policies, we're looking for the hello interval. My mistake there. Let's continue through this a little bit. And we see here we've got the name, network type, priority, interface cost, interface controls, and the hello interval. That there's our hello interval there, and our hello interval is 10. And then there's a comma, and then there's the dead interval below it, and that is set to 40. 4 times the hello interval, as is standard for OSPF. And that just briefly here we can see that the interface controls, we have an array of advertised subnet, MTU ignore, BFD, and passive participation. That this includes the policies used for configuring OSPF, that the APIC, the controller, will use that policy to actually implement OSPF on the device. But we see that the hello interval here is 10, so our answer will be B, 10. I hope that this has been informative for you, and I'd like to thank you for viewing. Configuration management. Configuration management systems are something that allows centralized management of your configuration for your devices. Now, this has been used for servers for a long time by system admins to manage the state or configuration of very large groups of servers. So you have many web servers, and that there are several steps that need to occur from the base operating system installation in order to get that server ready to participate as a distributed node in your server cluster. That your configuration management system can go ahead and apply these steps after that initial base installation and get that server ready for you as an automation tool, but also as a method of setting your infrastructure as code, making it very repeatable. So this has been used for servers for a long time, but more recently this has come to apply to network devices, and specifically as the CCNA is concerned, we're going to be covering 3 different configuration management systems. That Cisco wants you to be familiar with these and understand where their differences are, so you can be familiar with the capabilities of each one. So with that, let's go ahead and jump right on in here. So the 3 management systems we're going to be covering are Ansible, Puppet, and Chef. Now, configuration management systems, they allow for verifiable configuration states to be scaled. Now, like I said, this is often referred to as infrastructure as code. And that's the whole goal of automation, right? Is to do your configuration once, to write it as code, and then have it be applied many times. Is to take away any repetitive tasks, like going through and actually entering commands in at the command line, and just let your configuration management take care of this. That you create your configuration, your base configuration once, and then have it apply many times. And that this is generally done per device role. So all of your access layer switches will have a very similar configuration. All of your distribution layer switches will have a very similar configuration. Your interdepartmental routers will have a very similar configuration, so on and so forth, that you might just change the IP addresses or the VLANs a little bit here or there, but that's going to be about all. That everything else for setting your SSH server or your usernames, passwords, all of your security options and policies, and your QoS and things of that sort are all very standard, and it's a standard configuration template. That this not only allows for the automation, but really allows for auditing very, very well, is that you can audit your configuration drift. Say that you have admins throughout your organization that have a tendency to go through and just make changes on the fly without going ahead and going through your change management process. That this really allows for auditing your configurations very well in a centralized manner, in a way that's reportable, so that you can confirm that your configurations actually conform to your policies. And this can be very awesome in a industry where you have a lot of compliance regulations that you need to abide by, and that you need to supply to your auditors from time to time samples of your configuration or samples of your policy and how you have gone through to ensure that this policy is actually being met. So that's what's awesome about configuration management, right? Is that you have centralized configuration for each device, and that it applies and can verify that your configuration is actually the one that is centralized at your central server. Now, the reason why I haven't gone into much detail here is because Ansible, Puppet, and Chef, they go about this in a slightly different way. Is that they pretty much perform the same task, the thing I'm talking about here of configuration management, but they really differ slightly in their capabilities and the architecture and how they achieve this. So I'm going to go ahead and wait until we talk about each one here to really talk about the details as to how this happens. So with that, let's move on to the next slide here. And the first one we're going to be talking about is Ansible. So Ansible, where Ansible really stands out is that it's agentless. It only uses SSH to configure the devices. Now, what this also means is that this is a system where you need to specify the individual commands that are to be run on your device. That Ansible uses the concept of playbooks, and that your playbook is written in YAML, and it describes the tasks to be performed on the device. So here we have in this sample playbook that this is a playbook applying to the group of hosts called routers, and that we can say whether we want it to gather facts as well. And the tasks, we have first one task here that is called configure SNMP string on all devices, and we want it to save the configuration on the device when the configuration has changed, right? So the configuration may not necessarily change, as it's going to log into the device and try to apply this task at whatever specified interval that you do, and or on demand as a push, because it's actually connecting and applying these configuration commands. And in the event that these commands cause any change to the config, if these commands were not already present, then it will go ahead and save that configuration. And then you can see, and I'm sure you're familiar with the commands that are being applied here, is SNMP server community read only, RO, is that our community for SNMP is read-only, and it only has RO permissions, or read_write has read-write permissions. We are setting the domain name, IP domain name, to roger.com. We are enabling traps, and that we are setting our syslog server to 10.0.100.77 here. And that's the end of our playbook. Now you can imagine we can have several tasks here, right? To go ahead and apply the standard usernames and passwords, to apply the standard security policy, to apply the QoS policy. And that could be on our set of hosts named switches if we wanted. Now you can see how this could be very scalable, is that we can have it to different sets of hosts. We could have it applied to ASAs and set our standard firewalling options or web filtering options, so on and so forth. And that we see here, after we have applied the configuration, that this is actually a different playbook that was run, that this was on switches, on access switch 1, 2, 1, 2, and that there are one task that was done, and the one task ended up giving us an OK that it applied successfully, and that one task ended up causing a change in the device. And same thing for ASW2, is that the one task gave us an OK, and that one task applied a change. Is that none of these 4 devices here ended up having the commands that we specified in our playbook, and that our changed increments with the number of tasks which resulted in a change. Now, we don't know which of these lines specifically actually ended up in a change, that it could have been any one of them, or it could have been all of them. We just know this entire task is something that caused a change, and therefore it would have resulted in a save, and it ended up being okay, that it did not fail and it was not unreachable. Now, we could have had multiple tasks here. Let's say we had 3 tasks, and that 2 of them were successful and resulted in a change, and 1 failed. Then we would have seen here this 1 would have been a 2, this changed would have been a 2, and this failed would have been a 1. That's how this play recap is written out here. And that if all 3 tasks resulted in a change and all 3 were successful, then OK and changed would both be a 3 here. That this is stating for each task that was applied on each of these devices what was the result of that task. Now, YAML is a language that's used for, the explicit definition of properties here. That's something to be familiar with if you were going to go through with using Ansible or trying it out. You might want to go ahead and look that up and do a review of the YAML scripting language. Awesome. So that's an overview of Ansible here. And actually, I forgot to mention that until recently, it will take credentials at the command line entered by the user. So when you go ahead and create your playbook here, typically, as you could see, you had your hosts list of routers, and that list was a list of IP addresses, and then also the usernames and passwords for each of those devices, and that you could specify one set of username password for the whole group of hosts or for each individual IP address. Now, of course, that means that you are saving your usernames and passwords in plain text on a file on your Ansible server, and that is not really awesome. That what you can do as well is Ansible allows you to run your playbook here, and that you can specify your password at runtime of the playbook. So then you can tell Ansible to run the playbook, and it'll ask for the password, and you can type it in then. And as you can imagine, this is not necessarily something that you would have run on a schedule. This is something that perhaps you, as the network administrator, would go ahead and run on demand. That if you had configuration changes to apply, you could run that. If you wanted to verify the configuration on everything, you could run that. If you just wanted to see exactly which tasks here ended up resulting in a change as to what the drift from the configuration was, you can go ahead and run this on demand. And then in your play recap, this is just a small section here of the whole play recap that Ansible gives out, that it also specifies the resultant of each individual task. Awesome. Let's go ahead and move on to the next configuration management system here. That's going to be Puppet. So unlike Ansible, Puppet requires an agent to be installed on the device to manage it. Now, really think about what that means here, is that we need a piece of software installed on our device, on our network device, that is running as a Puppet agent in order to manage that device. Now, as you can imagine, this causes a lot of compatibility problems, right? Especially for older devices. If you have your Catalyst 3550s, or your 1941 routers, that you probably don't have an agent software available that you can run on there. I'm not aware of an agent that you can run on these devices. They are getting better at creating more compatible agent softwares that can actually apply to these, but really what you're going to be running this on is Nexus switches and perhaps the Cisco ASA. Firewalls, is that these do allow for the agent to be installed. There is a available compatible agent, and that you can manage these devices. Now, Puppet uses its own configuration language that was inspired by Nagios, and it's built on Ruby. So it would be good to be familiar with Ruby if you're going to utilize Puppet. Now, Puppet also has a version available called Puppet Enterprise, and that does have a graphical interface available. However, your configuration creation, so here's an example of a manifest, and that's the term that Puppet uses, is that you apply a manifest to a device, is the manifest creation is still done manually, that you do still need to code up your manifest in a text editor of sorts in order to apply that with Puppet, but then your actual application and reporting and auditing can all be done through a graphical interface with Puppet Enterprise. Now, as you could probably tell, this manifest looks a lot different than the playbook of Ansible, and that it's a declarative manifest where the desired state is configured rather than individual commands. That we have here that we want the OSPF VRF configuration to have the auto cost of 46,000 and the default metric be 5, and that we want our Ethernet 1/2 interface to be in area 200 and to have a cost of 200. We're not stating the actual commands that we want applied on the device. We're stating the state, the desired state of the device, and then allowing Puppet to figure out the individual commands that need to be run. The interface Ethernet 1/2, IP OSPF area 200, so on and so forth, that these individual commands are left up to Puppet to figure out, and that we're just giving it the end result, the desired state of the device. Now, Puppet's architecture is that the master server manages the nodes with the agent installed. So remember, the agent is installed on each of your managed devices, and that you have a master server, which is the one that all of the agents check in with and can push the configuration to the agents. Now, managed nodes check in with the master every 30 minutes by default to verify their configuration. That every 30 minutes, the agent will check in with the master server, and it will check the declarative manifest here and see if its configuration matches what is stated here. If it does not, it will conform its configuration to what is stated here. So your configuration management must be done at Puppet, that you cannot make changes at the individual device, or else it will be reverted very shortly later to whatever configuration is specified at the Puppet master server. Now, Ansible, of course, does not do this. Because it does not have an agent, and it is a push-only system. That Ansible must connect to each individual device by SSH and apply the commands. And then it is recording the result of those commands so that you can do reporting and auditing on the configuration on each device. Awesome. So that's how Puppet works. Now let's go on to our last of configuration management system here, and that's Chef. So Chef's architecture is very similar to Puppet in that it requires an agent to be installed on the device. So again, you're going to run into your compatibility problem with your older devices, and that can be okay if you have a newer infrastructure and you're using a lot of NXOS switches. Then awesome, this is great. And in fact, the newer Catalyst switches, I believe the 6509, also supports the agent here as well. And that, like Puppet, Chef is also built on Ruby. So that is a benefit here as well, that if you're going to go for one of these two, learning Ruby is not a bad idea, that you can go ahead and be able to work with these a lot easier, or at least learn the basics of Ruby. Just like Puppet, Chef also uses a declarative state. Now, these are called recipes and cookbooks. Is that they use the whole chef and cooking theme with Chef, with the recipes and cookbooks and applying a cookbook. Now, where Chef has a major difference is that the cookbook processing occurs at each agent. So with Puppet, let me go ahead and clarify this, is that with Puppet, the agent connects to the master server, and the agent sends its current state to the master server. The master server computes the differences, if there are any, between the configured state and the current state, and it will send back to the agent what the desired state is so that the agent can apply that state, or will send it the commands that need to be run. With Chef, what happens is that the agent connects to the master server, or connects to the server, and that it just pulls the cookbook. It pulls the desired state. And then on the agent, it is processing the desired state and comparing it to the current state to confirm whether it conforms to the desired state or not, and will make changes as needed to allow it to conform. Chef does not have a push model, that you cannot push the desired state to the to the agents. That it must pull, because the configuration change is being done at the agent, or the comparison is being done at the agent. This makes quick changes pretty much impossible. That when you go ahead and set a new recipe in your cookbook, and well, you're just going to be waiting until the agents check in again. And this may happen across your network quickly. It may not happen quickly. It depends on how often your agents are configured to pull from the server. Now, this does allow for a very distributed and extremely scalable system, is that your central server is no longer a bottleneck point, and that it is very lightly used. It's only used as a repository, really, for the agents to pull the desired state from, and then the agents are actually doing the configuration calculation. Now, this example recipe here is for NXOS switch ports and configuring them. That we see here, we have the interface Ethernet 1/1. And we are doing some configuration. We are creating, and we are setting the IP address, the net mask, whether we have proxy ARP enabled or IPv4 redirects enabled, and whether it is shut down or not, and whether this switch port mode is enabled or not, if it's switch port or no switch port, a layer 3 or a layer 2 interface. And then for Ethernet 1/2, we are setting it as an access VLAN 100, and that it is not shut down, and that it is a access switch port, not a trunk, and that whether we want VTP turned on or not, for VLAN trunking protocol. and that you can see that this is a very similar kind of configuration, is a declarative state configuration, much like Puppet, but that the actual syntax for that configuration is much different, and it is something that you would need to be familiar with if you're going to be writing your own configuration. There are a lot of templates available for all three of these configuration management systems, Ansible, Puppet, and Chef, that if you're going to try out any one of them, they are all open source, and that you can try them out for free, and that you can go and get templates so you can get up and running very quickly and be able to try them out and see whether these are a good fit for your organization or not. Awesome. Thanks for hanging in there with me, everyone. Now let's go through a couple of practice questions before we end off. First up, of the three configuration management solutions below, which does not require an agent on the managed device? Is that Chef, Puppet, or Ansible? Now, you should know by now that Ansible is the one that connects via SSH and does not require an agent, that the other two here do require an agent, and because of that, Ansible is the most compatible with older devices and the most compatible with third-party devices as well. That Ansible really can be used in almost any environment, whereas Chef and Puppet, not quite so much. You need really particular devices in order to use those, but I wouldn't shy away from them anyway, that they could have a good use in your organization anyway. I'll go ahead and check out their compatibility lists and see if it's a good fit for your network. And finally, which options below employ a declarative state structure, where the device state is defined, rather than specific commands to run on the device? Is it Puppet and Chef, Chef and Ansible, Ansible and Puppet, or none of the above, or a different combination? Now, Ansible, because it connects via SSH, it ends up applying individual commands to each device. That Puppet and Chef, because they use an agent, they're able to do a declarative state structure, and therefore the answer here is A, Puppet and Chef. Now, I hope that this has been informative for you, and I would like to thank you for viewing.